Hello, sir. Shall we start? Upendra sir.
Devendraji, I am ready as you say.
Okay, okay. Thank you so much. Okay, dear participants, good morning to all of you. So I once again welcome you all in the first session of day 4. So today, Professor Rupender Singh from NITTR again with us, and today he is going to discuss about the materials for 4D printing. So today you will learn the different aspect of 4D printing, because till now the different topics on 3D printing has already been covered. So today this topic will be very interesting for you. So now I hand over to Professor Singh. Sir, I welcome you.
Thank you, Narendraji. Once again, I am really thankful to the coordinator and the department at NIT Jalandhar for giving me this opportunity. I hope that this discussion will be really useful for all of us, and if we have, a lot of interaction and discussion, then this will be better for my understanding also in this area. So, with the permission of chair, let me share my screen.
Please, sir.
Yes, sir, please share.
So, whether the screen visible?
Yes, yes, sir. Yes, please.
Okay. So, dear friends, let us start the proceeding for today. This session, the focus will be mainly on the smart materials that are helpful for 4D printing. So 3D printing, is now at the top of the town. Everybody across the globe is using this process, which may be probably be the replacement of our conventional manufacturing process in coming 10 years. As regard to Indian scenario is concerned, I personally believe that in coming 10 years, if not total replacement, the subtractive and additive manufacturing will go hand in hand, and lot of things will be definitely shifted to the 4D part. Specifically, if we are interested in some sophisticated, equipment, sophisticated products, specifically in the area of automation and robotics. Now, this particular discussion that we are going to make on 4D printing, we are interested in some 3D printed parts which can have some self-growing type feature as a function of time, and that property is the inbuilt property of some material. The component or the product may be functional prototype or non-functional prototype. It may be 3D printed or it may not be 3D printed. It may have the properties of the smartness. But the advantage with the 3D printed smart materials which will be having 4D capability is basically the design flexibility that we are having. I give you one example to put the attention of the people in this area of 4D, and then we will start with the further discussion. I have one of my collaborator at PGI Chandigarh, and we are working on some leg deformities. He is basically a surgeon, orthopedic surgeon, who is working on some leg deformities with the people with one short leg, maybe because of some accident or maybe by birth, some patient may have a problem. So what actually they do, if we have a case in which one patient is having the variation in dimension of the legs, right? So the patient may have a feeling of uncomfortable while walking or running or any other thing, right? So what they actually do, they basically cut the bone in the leg, right? And as a typical, mechanical engineer, we are quite comfortable with the word called spacer. So we put a one mechanical component between the two bones, which is a spacer. Now suppose the patient is in the growing age, so the leg dimension may increase, right? So the dimensions are going to increase. Now that spacer, if I can basically increase with a function of time in its length, right? So that will be, helping me in lot of post-surgical practices, and maybe using some stimulated environment, maybe using some magnetic field. If I am able to extend the spacer dimension, so overall the length of the bone is increasing in a controlled manner as the patient is increasing. So this is one typical example of 4D, and this is happening actually. These type of self-growing spacers, which are like, you just imagine as a typical mechanical engineer, we have a screw jack type mechanism in which we are allowing some screw to unscrew, and then there is an increase in the dimension. Now this expansion may be lateral, maybe at some angle, is through some stimulus by applying a magnetic field. So that particular increase in length because of the magnetic field as a stimulus is the 4D capability of that particular assembly. So now if I print that assembly using a 3D printer with lot of design flexibility, with lot of material characterization in mind, with lot of strength features in mind, basically this is the one of the breakthrough technology for these type of the patients. So these type of requirements are nowadays very common, specifically for some accidental patient, trauma patients, right? So there is a need for understanding how I can grow my 3D printed part with some stimulus. So that is the theme around which this whole discussion will move. So we are interested in some smart materials which can have a 4D capability. So let us start the discussion. So I think this figure you have seen so many times. This is from Chang and Chua paper, Journal of Advanced Manufacturing Technology, 2005, which says that rapid prototyping is additive type, combination of additive and subtractive, and then it can be subtractive type. And under additive, there can be various technologies: stereolithography, digital light processing, FDM, SLS, 3D printing. Similarly, I can have a combination of additive and subtractive, in which some CNC combination with the different additive manufacturing processes going on. Again, with the basic 3D printing, some CAD file going to 3D printer, then we are getting a 3D printed part. Now, what is the 4D in this 3D printed component? Now, 4D printing by definition is the printing of the smart material. So what is a smart material? Let us understand it from the very basic. What is a smart material? From where this smartness will come? Smart material is, to understand the smart material, let us take the example of a sunflower. When there is a sunrise, right? So the flower faces up, and as there is a movement of the earth around the sunflower always faces towards the sun. So there is an angular movement. You just imagine there is up-down movement. So during sunset, again it faces down. There are many such flowers, across the different geographical locations across the world. You can see which are opening up their parts once there is a sunlight. So once there is a period of the sunset, they again closes down. So there is some stimulus which is in the form of sunlight, which basically actuate some mechanism as a function of time. So this is a representation of the fourth dimension. So 4D is not printing in 4 dimension. This is the 3 dimensional part only, but it is growing or changing its dimension, some shape changing, some volume changing, something like that as a function of the time. So smart material printing is basically categorized as the 4D printing, right? I give you one typical example from the mechanical engineering point of view. All of us are quite comfortable for understanding the concept of dynamometers. So dynamometers we use in machining, maybe on lathe or milling or shaper, basically to know how much force is there, right? So if you see how the dynamometer work, and normally the commercial dynamometer are either strain gauge based or they are piezo based. And in piezo based dynamometer, we are using some quartz crystal, and once I put a load over the quartz crystal, its dimension increases. So once the load is removed, it comes back to the original dimension. So applying a load, changing dimension, releasing a load, coming back to the original dimension. Now this basically change in dimension or the change in length or width or thickness has been calibrated for the amount of the load applied, and we are using these type of arrangement for measurement of the forces in x, y, and z direction while we are working on the let us say some machining setup, maybe on lathe, maybe on milling, maybe on shaper. Now you just imagine there is a crystal of quartz which is having this piezo property. Now suppose I print some I have some 3D printed part which is once I put a load, it increases its dimension. Once I release a load, it comes back to the original dimension. So this is a something behavior of a 4D, right? So in this case, what is the stimulus? The stimulus is the load. Now, typical example from the polymer side, we have, once we talk about the fuse deposition modeling based 3D printing, we normally talk about the material called ABS, PLA, PA6, LDPE, HDPE, these type of thermoplastic material. We have one more very good material that is called PVDF. So this PVDF is basically a piezo-based material which is having a property similar to that of the quartz crystal. So what is this PVDF? In this PVDF, basically we have a carbon-carbon chain, and alternatively on the each carbon I have a hydrogen and fluorine. This is polyvinyl difluoride. Right now, if I apply a load over this PVDF crystal, which is available in the granule form, right? So what will happen? The alternative hydrogen and fluorine, their arrangement changes to all hydrogen on the one side of the chain and all fluorine on the other side of the chain. So we call this that with the application of the load on this PVD crystal, the alpha phase is changing to the beta phase. Just imagine there is a carbon-carbon chain, hydrogen fluorine on one side of the carbon chain, then on the lower side again hydrogen fluorine. This is the alpha phase. Now apply a load. Now this alpha phase is changing to the beta phase, all hydrogen on one side and all fluorine on the other side. So there is a charge level like a van der Waals forces. So we get a property like compaction and expansion if I again convert from beta phase to alpha phase. So this is basically the inherent capability of this material that is called PVDF. If I print this PVDF with the application of the load, I can control the change of alpha to beta. So if I change the phase from alpha to beta, what will happen is contraction and expansion capabilities. These are basically helping me to develop some transducer, right? And that is basically the 4D part within this material. Now another important thing is this piezo behavior, which is similar to the quartz crystal, for which I am going to make some dynamometer. This piezo behavior, that is changing phase alpha to beta in the PVDF crystal, can also be executed with the use of the voltage. So at high voltage, right? So we are getting the similar behavior. So what I want to say from this, the stimulus is important. It has been observed that for the different type of the polymers, there are the different type of the stimulus. Specifically, like for this type of the material, the stimulus is load, the stimulus is voltage. Now you just imagine if I apply both, what is the effect? So there will be a different level of compaction and expansion, right? So basically, if I print this material as a smart material, it can change its state, it can change its dimension, it can change its color or some other physical feature. But once I reverse this, I can come back to the original position. So changing from one phase to another, then coming back to the same phase with same stimulus or with some other stimulus. If this is there, then we call it as a 4D property of the material. So a material which can change its physical state after solidification, maybe, then when it is triggered by external stimulus, the stimulus can be in different form. We call it as a smart material. So broadly what we say, this 4D printing is an extension of the 3D printing, and any 3D printing part becomes 4D once we add the fourth dimension into it. So what is the fourth dimension? Basically, as a function of time, some material is growing, or in the form of expansion it is there, or some compaction is there, or some other property. that is changing, but that is reversible. So if it is there, I have a repeatability, I have a reversibility, then we call it as a 4D material, right? I will show you some of the case studies where how 3D printed parts we are able to get the 4D capability and how to program it. There are some types of the programming, one-way programming, two-way programming, that we will see in terms of the case study. Another way to understand this reason for smart material, it can be the intrinsic property of the material. Like I have already explained, some material have a inherent property like this PVDF. This is having a carbon-carbon chain, then alternative hydrogen and fluorine in the form of alpha phase. Apply a stimulus, maybe load or the voltage, it will be converted into the beta phase. So alpha phase to beta phase, once it is converted, so there is a expansion, again change the voltage, come to the lower voltage, again come to the alpha stage, we will have a compaction, right? So this is the inherent property, so we call it as the intrinsic property of the material. Then sometimes the material is not having the intrinsic property, we want to add that property to this material. So this extrinsic property, once we want to add some property to this material, this extrinsic property is based upon the external factors. So the external factors, like for example, my polymers are non-conducting in nature. So if I want to make the polymer conducting, I can do some reinforcement of, let us say, graphene. I can do some reinforcement of aluminium. I can do some reinforcement of copper, which is a conducting material. So through reinforcement in the material, I can basically add the smart material, smartness in my material. Right? Polymers are non-conducting either thermally or electrically. Do some reinforcement, so they will become conducting. Right? So we can control some features. Then there is another concept that is called the concept of the metamaterial. So this metamaterial concept is quite common with our civil engineering friends, but this is not very common in typical manufacturing area. So what is a metamaterial? Metamaterial is basically resulting into some enhanced property of the material, not because of the inherent property, but the length and the angle of the link through which some parts are joined together. I give you one example to put my point. All of us are quite comfortable with the concept of the trusses in our strength of material class. So once we used to study the strength of material, we have different beams, and then there are some links, interlinks are there. But we used to explain in our trusses section by taking the example of the railway bridge. Like otherwise, the railway bridge is going to be a solid section, but we want to reduce the weight, so we use the concept of trusses. So in trusses, there are different links, and their length is there, and the angle at which those links are joined. So that is basically responsible for the enhanced, maybe the modulus of toughness, enhanced young modulus within that structure, right? But the property of that structure is coming because of the dimension of the link, length of the link, and the angle of the link. Now I can have a flexibility in my design in which I am interested in less weight, but now the link and the angle I can control in my printing setup. Take the simple example of a plier. Now in plier that we use in our workshop, you just imagine the top part or the front part is going to hold something. The middle part is having some hinge type, and the end part is really open. There we are going to apply some load. So if I just bifurcate the three zones, so all the three zones will be requiring the different quantity of young modulus in value. Like at the lever end, I may be interested in some compressive property. At some hinge end, I may be interested in some flexural property. Then in the front end, I am interested in some different property. Now what I am going to do is I am going to print the whole assembly in three different zones. Initial zone with some other infill pattern where I will get a different strength. Middle zone with some different infill pattern, infill density. In typical polymer printing, I can control around 15 parameters through the software. So basically, which property is required at which section accordingly I can print. So this meta material is definitely going to help me in getting the 4D property within that material, right? So this is the one of the recent advancement, and we can print this 4D based prototypes very easily using our conventional open source printers. Okay, now the point is, how to program. So there are probably the three ways of programming. Like suppose my material is in state A. This is a 3D printed material. I give some stimulus to it, so it goes to the state B. Then I give another stimulus, it can come back to the state A. So this is a one way of programming, right? We can have some example for this. Let us say I am interested in some structure where I am having a controlled. I am requiring a surface roughness or the porosity to be controlled. So I give some chemical exposure. So surface roughness is improved. Like in case of typical 3D printing for the polymer part, if it is made up of a ABS, we give exposure of the acetone, right? So chemical stimulus is there. Then to have a better dimensional stability, we basically put that component or that part at some temperature below zero, right? So again the temperature is the other stimulus. So I get a finish or improved porosity, right? Initially, if it is a 3D printed part, it may be in microns, but once I give this type of exposure, this may go to the nano levels, right? Now I am interested in reversing this. So what we can do, since this ABS material is having a glass transition in the range of 105 degrees Celsius, so I can again give exposure of high temperature, then again the surface will become rough, there will be more porosity, and I can do this number of times. So I can change the state, right? So this is a one way of programming. We will show you some of the case studies to understand in a better way. Then there is a two-way programming. Some material is in state A. I give some stimulus on, it comes to the state B. Reverse it, it will come back to A. Simple example is using a magnetic field. Like at the starting of our discussion, I have given one example of leg deformity. Right? Suppose there is some patient, we want to increase some dimension of the in the spacer, right, for the leg deformity. So you are putting some magnetic field on. So with the effect of magnetic stimulus, some material is expanding. Right? Now just reverse it, it can contract. So this is a two-way programming. Then there can be a multi-stage programming. With one stimulus, I am shifting from A to A1, then A1 to A2 another stimulus, then A2 to A, then another stimulus. So I can have a stimulus at different levels, right? So you can think of multiple stimulus, use of multi-stimulus and multi-stages. So this is the technology that is very much understandable now, that there is a thermoplastic spool. This feedstock filament is entered into some liquefier chamber. We are heating this, then layer by layer material deposition is there. So I'm getting a 3D printed part, and then there is a concept of sport material and build material, and finally I can put into some ultrasonic chamber, clean it, and finally get a finished part. Now how we can use it for 4D printing. Now this is the first case study that I'm going to explain this work that we have done under the DST project. So the idea is the multi-material additive manufacturing or 3D printing for sustainable innovative materials and structures. We are interested in developing some innovative material, and of course if I am having an innovative material, then the next stage is to have an innovative structure. Now how this works? Okay, since we are interested in structures, so for the non-civil engineering people, let us understand the structures in our country are classified as per CPWD in three types. One is called grade 1 structure, grade 2 structure, and grade 3 structure. So grade 1 structures are those structures which are of international importance, like the Taj Mahal, and this is being controlled by the government. There are different agencies which are taking care of these type of monuments, like Archaeological Survey of India. Then there are grade 2 structures which are also of national importance and managed by different state or the central government. Then at the end, we have the grade 3 structures. So grade 3 structures are also having their heritage value, their cultural things, how the cultural grow in that particular area, that is being reflected through these type of sites, but these are not controlled by the government. So one of the figure that I'm showing to you, this is the grade 3 structure over which we are working, because the simple reason is this is less regulated. Normally there are a lot of private structures throughout the country where you can think of putting your idea of adding the smart meters. Otherwise, for grade 1 and grade 2 structures, if you want to do some iteration, lot of procedure we have to follow, and we have to give a proof of concept also. But for grade 3 structures, they are quite liberal. So for the basic research, for putting the a proof of concept, normally people work on the grade 3 structure. So this is the one of the grade 3 structure that is in front of you. This is in village Kundani Kala in district Ludhiana of the Punjab state. So what actually we are doing, this is the structure that has been built in something around 1898, right? Now, this is one of the heritage structure, grade 3. Now, what is the idea? What is the research part in this for 3D and 4D printing? So, just imagine this is the wall of the heritage structure, which is accessible to me, and this side of the wall is not accessible to me, right? Suppose it has a cavity like this, right? So, I have to fill this cavity so that the crack propagation is not there, and finally the structure may not collapse, right? This is one of the serious issue in our country or across the world, like how to preserve these type of the heritage structure, because it represents how the culture has grown up, how the things have come better in the previous period of time, right? So one of the basic things that we have to understand, before 19th century, this is a general statement. The different structures that have been prepared, they were not using the cement in the way we are working right now. Because if you see how the cement is prepared, basically cement is prepared from the limestone. So limestone is basically CaCO3, calcium carbonate. Once we heat it up to 1400 degrees Celsius, it leads to CO2 plus calcium oxide. Now this calcium oxide is basically called clinker. Now this clinker is basically reinforced with gypsum, and then we do the crushing in the ball mill, and we get a final cement in the form we want, right? Now the structure that has been prepared before 19th century, the people were not aware that for getting the better quality of clinker and then mixing it with gypsum, I have to heat it up to 1400 degrees Celsius. People were knowing that we have to use limestone, but the processing is not that way, and the blameness basically, which is a reciprocal of the density, is not equal to what we are using nowadays, right? So you can well understand that the cement powder is very fine, so it gives a different level because the blameness is high. It gives a different quality of bonding capability. Now, for those structures in which the material for binding is not the cement, we have to be little careful. So this is one of such case, right? So here the cavity is there. Now suppose I want to fill this cavity. So one of the solution that has been provided by one multinational company called Hilti, HILTI. This is a German-based multinational company. They provide some epoxy-based solution. So what they do, if you have a crack development, and this is a non-cement based structure. So what they do, they have a epoxy. Now you force that epoxy with the some plunger type arrangement, and finally you can fill the cavity, and the area that has been created or some void is there, we can fill it. So this is possible. Now there is a second case when the entry side of the crack is large, but on the rear side the crack is small. Again you can fill this. But now there is a third case when the entrance is small, but on the rear side you have a large cavity, you have a large volume. Now if this is the case, sometimes the epoxy may not fill all the interstitial sites. Or if the crack is irregular in maybe in upward direction or maybe in downward direction, the epoxy may not fill the all interstitial sites. Now for these type of the cases, like the heritage structures, we have to give some solution. Like take the example of the Golden Temple of Amritsar. The structure was built in 15th century. So at that time, the limestone, of course, was used. But now just imagine if the structure needs a maintenance, you cannot close it down for a long period of time. Right? So as a lot of people are moving to that place for religious reason. So what we have to do is we have to have some offline solution. So something is prepared in the lab, and finally that product you are going to assemble at the site, right? So what we are doing, what are the steps? Basically, first is the crack detection by 3D laser scanning. So I will detect the crack. I will detect what is the volume, what is the size of the crack. Then 3D printing of the smart materials. So some smart material I want to fill, and finally do the assembly. So how I will do the assembly? This we were really fascinated from a Murthy workshop. So just imagine you take your car to the some workshop like Murthy or any other automobile workshop. What they actually do, they hold your vehicle on a lift, which may be hydraulic or pneumatic lift, and they lift the car up, right? So the operator, depending on his height and his comfort, basically lift the car in the upward position, and then they unscrew all the tires, right? And for unscrewing that, they have a pneumatic gun. So for that pneumatic gun is basically can have a clockwise movement if you want to screw up, and it can have a anti-clockwise movement if you want to unscrew some nut or bolt, right? So similarly, if I can just change the direction of the movement of some nut or bolt with a direction of the flow of the compressed air, so I want the similar thing. Once I want to add some material into this smart material, it should be compacted so that it should enter easily. So once it is entered, now it should grow and take the shape of the cavity, right? So it should grow and give a push fit type solution rather than a adhesive type solution. So that is the idea of using a filler and the assembly of the smart material. So we have printed some thermoplastic part which is smart enough that can be compacted, put into the cavity. So once it is inside the cavity, then increase the dimension, so it will take the shape of the crack. So that is one of the alternative of the epoxy solution that has been in market, which is based upon the adhesive nature. So that is the 4D part as the growing part. Now suppose the intended function is over, or you want to again remove this, then again give some stimulus, which in this case is the magnetic field, so that the part that has already expanded, it is compacted, and you can remove it. So it is easy to remove. So these are another some of the structures over which we are working. These are some of the bridge structures. Now this is really important to see. Uh, all these bridges are the British period bridge. You can see in these structures, I have a arch structure, right? So in these type of arch, I have a compressive loading condition on this axis, then the tensile loading condition on the upper axis. But the whole material is a single composite material, right? So I can think of a multi-material printing in which if I am interested in a situation where I am requiring a better compressive property, that material has been put on the lower side of the arc, and in a case I am interested in better tensile property, that has been put on the other side of the arc. So this is the another site over which we are working. This is the Sarai Lashkari Khan. This is near Doraha in district Ludhiana of the Punjab state. This is something built in 1592. This in the Mughal period, right? This is the another site over which we are working as a smart offline solution for the upkeep of these type of these structures. Now to have a proof of concept, basically, we use three different materials. So one material is HIPS, the second material is ABS, and third material is PLA. So why we use this, that will be more clear from their basic property. The first property is their MFI. So till now, I think all of us are quite comfortable. What is the MFI? MFI is the melt flow index in gram per 10 minutes. So if MFI is more, basically I can have a thin section printing. If MFI is less, the section to be printed cannot be really thin. This will be a thick section, right? So we measured the HIPS MFI. This is the observed value, which was 7.5 gram per 10 minutes. Some standard deviation and standard error values have been calculated. For ABS, the MFI is more. Now, if I compare HIPS and ABS, I can simply say the section with ABS can be thinner, can be printed thinner as compared to the HIPS. So there is a variation. Similarly, if you just see the PLA, further the MFI is more. That means if I keep same temperature condition, same feeding condition, the section that will be printed by PLA will be much thinner as compared to of the HIPS as well as of ABS. We also, printed their tensile coupons using ASTM D68 and their flexural coupons. And what we observed, the young modulus of HIPS, that is particular grade of HIPS that we have used, this is high impact polystyrene, was 112. For ABS, that is acrylonitrile butadiene styrene, it was 175 megapascal, and for PLA it was much less. Similarly, other properties like yield stress, glass transition temperature. So you can see a significant change in the glass transition temperature 100, 109 and 62. Then other properties like peak load, peak strength, peak elongation, these have been initially measured. The point is I am going to use three different materials so that I can have a understanding of their compressive tensile nature, so that I can print some arch structure where the better compressive property at particular location is required. I can use that particular capability, right? So we use the open source FDM printer. Some of the parameters were kept fixed, like the dia of the nozzle, dia of the filament, height, layer height. Then I can control number of top and bottom layers. These all are easily controlled by the software. Then the infill pattern, whether you want rectilinear, hexagonal, octagonal, there are different type of patterns depending on the type of software we are working. Then the perimeter speed, travel speed, extrusion temperature, print bed temperature, these were kept fixed. Now, but what we vary, so that is important to understand. Like for printing some tensile coupons, like we have a ABS as the top layer, then PLA as the middle layer, and HIPS as the bottom layer. In another case, PLA in the top, HIPS in the middle, and ABS at the lower one. So similarly, in one case, the HAP was taken inside, so HIPS at the top and PLA at the left. So this is the multi-material printing. Now I am interested to understand, if I am using a multi-material printing, how this is going to help me in getting a better loading conditions under some compressive or the tensile loading conditions. Right. So for this purpose, we use a multi-layer printing, and the top layer was taken with one material, middle with other, and down with the another different material. And we use the DOE over here, using a Taguchi based optimization. Then other parameters were varied, like infill percentage and their printing speed. So these parameters were varied. So you can see these are the tensile equipment. Like in this case, the top layer was of PLA. In this case, top layer was of ABS. In this case, the top layer was of HIPS. So this is basically a load deflection diagram or the stress strain diagram. Once the whole material is a single composite, like all the layers, whatever we have printed, are of a single material. Like if I use a PLA, I got a typical stress strain curve like this. So this is the curve for PLA. This is the curve for ABS. This is the curve for HIPS, right? Now, once I did this exercise, I also tried to see what is their variation in the thermal property. I think we have one of the discussion in understanding the thermal property on the DSC analysis. So what we observed for these samples, by giving the temperature from room temperature, let us say 25 degree to 250 as in the heating cycle, then 250 to room temperature in the cooling, then from room temperature 250 another heating, then cooling cycle, as well as some time is lapsing. So what we try to observe, how much is the energy absorbed and how much is the energy released. Like for the ABS, it was taking 13.63 millijoule and releasing was 13.52. Then for PLA, it was 14.7 and releasing was 10.8. Then for hips, it was 11.7, and releasing was 10.87. That means the PLA, the energy has been, wasted in some other feature, maybe some phase transformation, something like that. So that this shows that PLA is relatively thermally less stable or unstable as compared to ABS and the hips in this case, for which I am doing the multi-material printing. Now, based upon DOE, this is the load deflection diagram or the stress strain diagram for the different materials that we have printed. Now you can see this is the stress strain curve for the hips. This is for PLA, and this is the curve for ABS. And from 1 to 9, all these curves are for multi-printed part as per our DOE. Now, this is the really important thing to understand. This is the microstructure of the different samples that has been prepared. Like in the first row, you can see this is at 30x magnification simply by optical microscope. This is the ABS printed part, right? So you can easily see the staircase effect is there. So there is a layer by layer deposition of material, but there is a staircase effect, right? In second case, I have a PLA printed. Again, there is a staircase effect. Then in third case, I have a hips. So in hips, there is another staircase effect you can see. Right now, you see in figure 1, the lower layer was of ABS. Then on this ABS, the PLA was printed. So once I have printed the PLA, what I am seeing over here, some globule formation is there. So some material, the polymeric material, there is a side flow, right? Then in the top layer there is a hips, right? Now if you see this row in serial number 4, once we have a PLA in the base, hips in the middle, and ABS in the top, there is no such side flow. So once you just imagine, I have a side flow of the material, basically my strength is compromised. Now I want to correlate this microstructure with my stress strain diagram. Just see for the curve 1 and 4. Now you see, if I see the curve 1, for the curve 1, this is the area under the curve, and for the curve 4, this is the area under the curve. So what I want to say is, if the area under the curve is more, area under this triangular surface is more, basically this shows the modulus of toughness is high. If modulus of toughness is high, my material can have a better impact strength under static conditions, right? So that means if I print the part with the same material, the material is same, but even the printing fashion is different, right? This material will be having less impact strength properties as compared to this material. So I can basically decide which material I have to print first, followed by the second material, followed by the third material for getting some desired property. Now, what is the takeaway or the logic for this is, the ABS is having some glass transition temperature to the range of 105. PLA in the 50-60 range, right? For the different grades it may vary, but generally in the range of 50 to 70. Now what will happen, if you first print the ABS substrate, 3D print the ABS substrate, then you are printing the PLA because of the difference in the TG. So the base is a little hot, right? So once the PLA is printed, so there will be side flow of the material, which is basically responsible for the reduced mechanical property or the reduction in the mechanical property. So I can basically decide which material I should print first, and their printing fashion we can actually control, right? So we try to see what happens once we have this type of the printing fashion. Now you just imagine I have a arch structure, so I can decide I need a compressive property better over here and tensile property better over here. Then there is some neutral zone. So accordingly, I can select a particular combination of material which can be printed to give these type of the desired features. So this has been tested for tensile coupons, compressive coupons. Then we also did the pull-out type test for ensuring this particular property in the material. Based on this, now I am interested in one way of programming so that I can understand if I am using a dual material printing for multi-material printing, how I can select the particular layer combination. So this particular case study is the extension of the work that we have seen just now, in which we are interested in printing of the dual thermoplastic with different layer combination, and I am interested in the tensile property, in the flexible property, and in their fracture surface investigation. So to put the proof of concept, basically we use the two materials. One is ABS and another is the PLA, right? And these have been multiple printed. And we introduce a new terms over here. One is called NOC and another is called NONC. So NOC is the number of conversion. Number of conversion means if I am changing some material in multi-material printing from one to another, and number of negative conversions if I am choosing the wrong selection of the material for my programming in the multi-material printing. So these are the typical, ASTM D795 and D638 standards for the flexible and the tensile specimens that has been printed. Now, to have a proof of concept, we use a simple, 3D printer, FDM open source. Some of the parameters were kept fixed, like bed temperature at the 75 degree, the nozzle temperature 200 degree, infill percentage 100%, infill speed 100 mm per second, number of perimeters 2, raster angle 0, layer width fixed, number of layers. Now this is important. This has also been kept fixed. So in this case, once we made a tensile coupon or we printed the flexible coupon, we have kept the number of layers as fixed, right? So their thickness, their width, everything is fixed. Now you see in serial number 1 over here, I have written as P P P P P P. All the layers, 6 layers, because I have kept the number of layers fixed as 6. All the 6 layers were of the single material, that is PLA, right? So that is why I have used the symbol P P P 6 times P, right? Then in second experiment, all the layers were of A, so 6 A's were there, right? Then at random, we use the concept of random number. We selected some combination of A and T. So in third case, serial number 3, the first layer was of PLA, followed by ABS, followed by PLA, again PLA, then ABS, then PLA. Now in this case, PLA, 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 ABS, ABS. Now there is no fashion. We have not used any DOE over here. We just use the concept of the random numbers. So at random, we try to understand, how your material is going to behave once we have a printing of multiple layers. So random layer we are basically interested, right? Now you see in serial number 10, first 2 layers are of PLA, then ABS, then PLA, then 2 layers of ABS, and we try to print some of the samples, like these are the samples, all the 12 samples for tensile as well as for the flexible property, and we try to see we put those samples on a UTM setup, and we try to see peak load, peak elongation, break load, break elongation, peak strength, break strength, and modulus of toughness. These are the experimental values, not the theoretical values, not the simulated values, but the printed sample values put on a UTM setup, and we try to break all the samples and try to see what is the actual physical value of all these mechanical properties. Typical stress strain curve you can see. So based on this, we come up with one logic that this type of material is following some fashion of breakage. So that breaking fashion is explained by two terms which may be new for us. One is called number of conversions and another is called number of negative conversions. So what is number of conversion? The number of conversion means if I am changing my layer from PLA to ABS, that is a conversion, right? So if I have some material, first layer of, let us say, PLA, then the another layer of ABS, so I have shift. So this is a conversion. So how many times in 6 number of layers I have the conversions, right? Now what is a negative conversion? Negative conversion is like you have seen in just the previous microstructure. If I print the ABS first and then I put the PLA over it, what will happen? See, there is a side flow of the material. That means the PLA layer must not be deposited over the ABS layer. So if I have deposited the PLA layer over the ABS layer, this is called negative conversion. So for the six different type of layer, how many number of conversions are there and how many number of negative conversions are there, we have to be really careful about this. Now you see in serial number 1, all the layers were of PLA. So P, 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 P. So there is no conversion. So number of conversion is 0. And also there is no conversion, there is no negative conversion also. So that is also 0. How many times P's are there? There were 6 P's. How many times A's are there? So there is a 0 A. Right? In second case, all were A. So no conversions, no negative conversion, no P. So 6 A's. Now see in serial number 3. So I have first layer of PLA, second layer of ABS. So P to A, one conversion, A to P, second conversion, then P to P, no conversion, then P to A, third conversion, and A to P, four conversion. So there were the four conversions. Number of conversions are four, right? How many negative conversions are there? So you see, P to A is not negative, but A to P is negative, one negative, so A to P another negative. So there is two number of negative conversions. How many P's are there? There were four P's. And how many A's were there? There were two A's. Now see in another example in serial number 7, I have A to A no conversion. So firstly there is no conversion. So A to P first conversion, then P to A two conversion. So there were two conversions, right? So how many are negative? Since A to P is negative, so number of negative conversion is 1, right? So there are how many P's and how many A's that we come to. So similarly in other serial number you can see in serial number 11, A to A no conversion, A to P one conversion, P to A two conversion, A to P three conversions. So there were three conversions, and how many negative conversions are there? Negative conversion is only once we have A to P. A to P here, A to P here. So there were two negative conversions. How many P and how many A's we can calculate. Now what we observe, if I am interested in typical mechanical properties, what we observe, the number of negative conversions followed by number of conversions followed by P and followed by A. If this is less, we get a better mechanical property, right? I am interested in multi-material printing, which layer to be printed on which surface. It may be a two material printing, three material printing with dual, triple, four times or more. This must follow the fashion that number of negative conversion should be minimum, followed by number of conversion to be minimum, followed by number of P to be minimum, followed by A. If we follow this, we get a better tensile strength, better mechanical properties. So accordingly, for the tensile, there is this fashion which is also followed in the flexural properties also. So we try to see their thermal behavior, which was also in line with the previous case. So they show better thermal stability. Similarly, the results were in line with the flexible properties. So we try to break on the tensile and the flexible part, and we try to correlate with their voids, with their surface roughness features, and they are also following the similar trends, right? So in this way, we are able to you can say the program our material for the multi-material printing case, right? Now this is the case with the multi-material printing and the programming feature of this type of the material. Now I will again take you back to the case study of the 4D printing, where we have used some stimulus for some self-assembly type application with some 4D capabilities, right? So as we have already discussed, the material may be under effect of some stimulus. There can be a one-way programming, there can be two-way programming, and there can be a multi-stage programming. And the stimulus can be load, it can be electric current, it can be light, it can be some magnetic field, it can be some chemical energy, it can be thermal energy, it can be some hydral effect, it can be hydrothermal, or there can be the combination of different type of stimulus, which helps me in controlling some behavior of the material. Now this is the case study that I am going to discuss with you. This is one of the work that we have done with our collaborator in Italy. This is the project of developing some smart tiles that we see in our kitchens or in bathrooms, which is basically a non-load bearing structure, and the customer requirements were four. Number one, they want to have a tile with a self assembly feature which can assemble self, right? So some sticking properties required. Number two, they they require these tiles for a location where the outside temperature is to the tune of minus 40 degree, right? So the government is providing some heat source so that the temperature in the cabin or in the house is maintained. So this is very common in the Western world, the provision of some hot air, right? But we want to conserve the energy or conserve the heat. So what we do is we do the paneling of the wood. Now, since the depletion of the natural resources is a concern, so we are no more interested in cutting more woods. So what we want the replacement of the wood. Number three requirement, uh, in most of the office cabins or even in the household region, we are using the PVC paneling. So once the life of the PVC is over, this basically adds to the plastic solid waste. Basically, some color is lost or there is some luster loss is there. So basically, this PVC paneling and that is there, we want to recycle that material. Number fourth requirement is we are interested in using some biocompatible polymer which is comfortable with humans. So keeping all these four requirements in mind, what we have planned, we will be using a PLA polymer which is biocompatible on the top layer of the tile, followed by some PVC on the second layer of the tile, followed by the wood dust in the third layer of the tile, and last tile which is going to be attached with the wall, it will be having some magnetic property, that is Fe3O4, and all these reinforcements will be blended in a PLA matrix, so that finally a composite type some tile I am preparing. Now this is the picture that you are seeing. This is for establishing the MFI of the composite. This is the extrusion to which I will be printing. I have printed the feedstock filament with different type of the layer combination, and this is the schematic for the 3D printing on the FDM. Now the PLA with the mechanical properties given in the table has been procured. Then PVC has been procured. This is the for magnetic properties. I have Fe3O4, right? And for then I have a good dust for the heat conservation type situation. So using all these, we printed the feedstock filament and we printed the multi-material tile, and we try to see what happens to the different properties that is required. So PLA, PVC, magnetite powder, and wood dust in different weight proportion were selected. So some extruder has been used with the different loading condition, like how much load I can put, then the composition, torque, temperature, and we try to see the first most important thing is the self-assembly feature. So how it is going to give a self-assembly? Just imagine I have a some wire frame, right? So in that wire frame, I can give some current to the tune of 12 volt, and so once there is a current, so I can basically control the uh, magnetic field. Now my tile is going to stick with that, right? So what I'm going to do is just before putting my assembly, let us suppose in a particular area in a XY plane, maybe in a vertical upward direction, I have to just let us say assemble the 100 tiles. So what I will do, just switch on the magnetic field, put the tiles, so they will be getting stick to it, right? So only that frame model, I will be having some fastening arrangement, so I can fasten that, right? And once my assembly is over, I can just switch off the current, and the assembly will remain as it is. Now suppose after a few days I am interested in some change in the design, right? So what I will again do, I can again switch on the current, right? So there will be there will be magnetic field because electromagnetic waves will be there, right? So I can disassemble all the tiles, right? And whatever the tile I want to disintegrate, so that I will just pick. The whole structure is not going to collapse. So there will be a lot of saving from the labor point of view. Now, how much my material will be having, how good the magnetic properties will be there. So we use the VSM testing, vibration spectrum magnetometry. So basically we try to develop the VH curves over there. So basically we have three type of properties. One is called magnetization, another is called corrosivity, and third is called retentivity. So magnetization is the composite material that we have developed, how easily I can magnetize, right? Then if I have magnetized that material, now I have switch off the current. For how long the material will be having that magnetic property? So that is called the retentivity. Now suppose I have applied the magnetic field in one direction, now I want to make it zero, and I have to provide the magnetic field in the opposite direction. So that is the corrosivity. So for the different proportion that we have used of the reinforcement in some composite material, how easily we can magnetize, how is the corrosivity value, how is the retentivity value, that help me in understanding the different proportion of that particular reinforcement. So that we have done some, analysis has been done, some, STEM based microstructural analysis followed by some EDS analysis was done, and based on this some proportion have been selected. So you can see we tried with the different combination like PLA, PVC with different weight proportion. Similarly, PLA reinforced with different proportion of Fe3O4 magnetite powders with different proportion of the wood. Those have been selected, and we try to see what is the peak load, peak elongation, break load, break elongation, peak strength, break strength, percentage elongation at peak, Young modulus, stress strain value for all different permutation and combinations. Then we have their stress strain curves, their hardness values, and their thermal stability also. Because if you are going to have a structure, typically in the civil engineering application, we need to understand how the thermal properties is there under different heating loading conditions. So in this case, the temperature from 0 to 200, and then 200 to again room temperature, again heating, again cooling. So number of cycles were there, and we try to see all these materials how they are thermally stable, right? So whether they are performing good in different heating cooling cycle, whether they are thermally stable. So this we try to establish, right? So what we observe that for the different materials in different heating cooling cycle, the composites are thermally stable. Then for different combination, we try to see their properties like uh, retentivity, magnetization, and corrosivity under different permutation combination, and we come up with a defined composition of these type of the material. So this is basically one of the case study in which we have a 4D property of a tile, right? So which is basically a composite. Here actually finally the product has been made. You apply a magnetic field, you give a current or the magnetic field, it will have a sticking property. Now you undo this, it will not be there. But the part, the design that is 3D printed, you have multi-layer printing, and with a stimulus as a magnetic field, it can have a 4D capability, right? 4D in this case is the capability which is similar to some adhesive nature, or you are undo the situation in which you can detach the tie. So this is the another case study in which the ABS has been reinforced with graphene, and we are interested in their 3D 4D capabilities, and we try to see their rheological, thermal, magnetic, and the mechanical properties. Like you see, in this case, we have reinforced different quantity of the graphene starting from 0%, 2.5%, 5%, 7.5%. So some graphene reinforcement is there. So with the reinforcement of graphene, their MFI value, some trend is there. Initially, there is a increasing trend. Then after certain level of 10%, the trend comes reversed, right? So there is a requirement of the study why this is there. So basically, to understand this, we need to go for the FTIR analysis, where we will come to know that how much maximum quantity of the reinforcement material can be there, so that carbon-carbon bond stretching is there. How much material it can accommodate, right? So this will be having it, or there will be a side flow of the material, so we can correlate with that FTIR peaks in this case. Then we try to see their thermal analysis, and what we observe with the increase in the graphene proportion, there is a increase in the thermal property, and we try to correlate with the magnetic properties of the material. So this has been correlated with the corrosivity, retentivity, and magnetization. And what we observed, as we are increasing this proportion, all the properties were increasing, right, to certain level, and then there is a decreasing trend. So I can have a thermal conducting ABS, which is a now capable of giving the 4D properties. Once I will give a stimulus of the electric current or the magnetic field, and this can be used for different type of the application. Now I'll show you another application in this case. We have worked on a material that is called PVDF. I have already explained that in PVDF there is a carbon-carbon chain with alternative hydrogen and fluorine, which is in the alpha phase. So once you apply a load or you apply a high voltage, this is converting to the beta phase. So this resulting into the piezo behavior of that material. Now, if you want to increase the piezo behavior of the material, we can have the reinforcement of some ceramic materials like barium titanate. It has been well reported in the literature that barium titanate helps in increasing the piezo property of that material. So that has been reinforced along with the graphene in this case, so that there can be better thermal and electrical connectivity. So what actually we did in the initial experiment, we use PVDF with 98% of by weight and 2% graphene. So this composition we call it as X, and barium titanate in different proportion like 10, 15, 20% we call it as Y. So X plus Y we try to find out their flow properties so that I should come to know how much thin section I can print with this type of material. And then again we use different composition of the material, and we try to prepare the feedstock filament, and that feedstock filament properties in terms of peak strength, break strength, modulus of toughness, this has been calculated. Stress strain curves were generated. Some one analysis was done, some thermal analysis at room temperature to some stressing temperature up to 250. In repeated cycle, we try to see whether the composite is thermally stable. And finally, we printed this on a, composite has been printed on a 3D printer, and we try to see their piezo behavior on in the terms of D33. So we measure the piezoelectric constant, and what we observed, we were able to get this piezo property from 20 picocoulomb per Newton to up to 65 picocoulomb per Newton. So this is sufficiently good for having some controlled behavior of this type of the material. So 65 picocoulomb per Newton is really good for measuring some force values in a typical dynamometer, right? So that has been 3D printed, and the piezo behavior is basically helping me to add the 4D capabilities in that material. So this is another case study in which 4D capabilities have been prepared in the terms of the shape memory property. Right, so shape memory effect is basically a 4D. So for this purpose, we use the PLA, and it has been reinforced with the ZNO. Right, so this ZNO is one of the smart material. Once it is reinforced in PLA, it can help me in getting the shape memory effect. Right, and of course it has the another capabilities which can also give me some result related to the semiconductor behavior of the material. But in this case, we use this for the shape memory property. So like in the previous case, I have a ZNO blended with polymer. So this is the extrusion setup, feedstock filament preparation. Then we try to see the thermal behavior in different heating cycle. Then we went on. We go for the reinforcement, 1% ZNO by weight, 2% ZNO by weight, and we try to see what is the effect on the change in the thermal stability, whether there is a change in the glass transition temperature. These things have been stabilized. Based on this, we printed the sample like this, U shape, right? So what we actually did is we took a virgin PLA sample, we put it in water at room temperature for let us say 5 hours, right? So we try to see what is the change in the shape. Basically, what we observe, this U becomes V, right? Then we again put that sample at the normal temperature condition in the room temperature, and we try to see what happens to this shape. So then that U become V, but there is a recovery. So what we observed, the recovery was to the tune of 85%. right? So again, the V was coming towards you, but the recovery was not proper, right? Then we did the same study at high temperature, around 40 degree, and what we observed, the recovery was very high to the tune of 97%. So that means there is a effect of the stimulus. The stimulus is here is the hydral and the thermal effect. That means some temperature effect is there. But once we have a different reinforcement of ZNO 1%, 2%, the recovery factor was improved. But this basic test help us in understanding that there is a effect of the stimulus, which is a temperature, which may be the hydral effect, basically the moisture in this case. So we try to see this effect at some elevated temperature, like above Tg, and at some low temperature at 10 degrees. So we try to see what is the effect in the weight change. Similarly, we try to see what is the effect in the volume. So what we observe, if I work on some extreme temperature conditions, like at low temperature, not at the room temperature, and then at some high temperature above the Tg of the material, the recovery was up to 99.9% in some of the cases. So if I print some material PLA with ZNO reinforcement, 1%, 2%, the recovery factor will be more. So I can use this material for some typical sensor application. So this is the 4D part in my 3D printed material. So why the material is behaving like this? So we try to correlate this with the porosity part. So we try to see their microstructure and the level of the porosity. And what we observe, once we have a better recovery, the porosity was basically improved with the effect of the stimulus, right? So now this is the last case study that I want to explain for the use of 4D printing as an extension of the 3D printing part for typical sensor application. This sensor we have actually developed for the mobile. Basically, this is in the form of antenna which can give the signal to the range of 2.45 gigahertz. This is basically the Bluetooth or the Wi-Fi range over which the data can be transmitted. Right. So in this case, we compare two things. One is the thermoplastic, that is LDPE, and another is the thermosetting, that is LDPE plus bakelite, that has been printed. So what we did is we collected the LDPE, that is a recycled one, and we reinforced the bakelite to it, and we try to see what is the effect on the MFI. So what we observed, some reinforcement resulting into the stacking of the material in the barrel, right? So based on this, we came to know how much maximum proportion of the reinforcement can be there in the base material. We went on different parameters like peak elongation, peak strength, break elongation, young modulus, for the different composition and different parameters, right? So this is the typical stress strain curve that we got for different composition. This you can see the feedstock filament preparation. This is the printing going on the open source 3D printer, and this is the sample for the version LDP. This is LDP reinforced with bakelite. Then what we did is we tried to develop a ring resonator for developing some sensor on this. So this is the 3D printed substrate, and on this 3D printed substrate there is a defined dimension of the ring. This is a standard test, a ring resonator test. So these are the copper film that have been printed over here, and we try to put the copper on this side as well as on the other side of the substrate, and then this is with the coaxial cable. I try to give some input of in the form of voltage or the current, right? So we try to excite this, and we try to generate the some radiation pattern out of this, and that has been measured on a vector network analysis. What we are getting is for the LDP, the first resonating peak was observed at the range of 2.75, and for the another case where the bakelite was reinforced, it was coming at the range of 2.87. So here you just see the bakelite is otherwise a thermosetting material which cannot be recycled, but this is giving me some peak signal at the range of 2.8 gigahertz. So this can be really used for some typical sensor application for some transfer of data. That is the function of the antenna. So we try to see what is the change in the resonating frequency. Once I have a change in the substrate material, we try to measure their dielectric constant. So there is a change in the dielectric constant of the material. Basically, this represents the charge capacity of the material. Then we try to using a software called HFSS. We try to see what is the trend in the peak variation that we got. Then we try to see what is the length and the width of the substrate that we can actually print, and some parametric optimization has been done for the gain of the signal, and finally we are able to print a antenna from the waste. And now this is going to give me a signal that can be interpreted for some different applications. Like one of the application I can share with you. If I use a biocompatible uh, substrate with a graphene coating over it, and then it is energized with some small battery, I can make a capsule antenna, right? A sensor, 3D printed capsule antenna sensor, and we are going to use this in some wild animals. Through surgery, we are going to put it in the some part in the body, maybe at some indoor location in the body near to some stomach part, right? So where which is not digested, of course, and I am going to use this data from the remote location where actually my lion or tiger is presently, so that there should not be a something like poaching, and I can also control their population. So where actually my wild animal is moving, so that can be actually used for understanding their behavior. So this is the beauty of the 4D parts. The 3D printed part can be used for numerous applications. We try to discuss some of the application from the biomedical part. Try to discuss some of the application from the construction part, specifically the structural engineering part, where we are having a non-load bearing structures, and of course the sensing part. That's all from my side. Now I will like to answer any queries if we have. So now this panel is open for discussion. Anybody who want to raise any query, I will really like to answer. Yes, please. If there are any queries.
Participants, if you have any query, then you can ask to Professor Jalandhar. Anyone want to ask?
Anyone from the participant, you can ask your question.
I think, sir, there is no query from
Good. Anyway, my submission at this stage is, if you have any 3D printed part, it may be a bio printed, it may be polymer printed, it may be metal printed. We can think of some stimulus which can actually change its dimension, change its volume, change its state. So this really adds value to the product, and that value added product is the requirement in the market. We can have some new product development through this. So that is the idea that I want to share in this discussion. Yeah. So Professor Mohit, if there are no queries, I think I may conclude. Yes, please.
Hello.
Yes, please.
Yes, sir. This is Muthu Kumar. I have one query, sir. Because we are preparing the. Hello.
On behalf of
Yes, please go ahead.
Yes, sir. We are preparing filament, right? Yeah. through twin screw extruder for some applications related with SMA. Also, we are going to add, right? Okay. For this, we prepare that wire. What are the tests to be carried out before we go for 3D printing for analyzing the properties of wire filament, right, sir?
Okay, if I am interested in 3D printing, so
Yeah.
the first basic thing is uh, before even preparation of the wire, I have to see whether my wire is having a properties or my material is having a properties that it can be well extruded or not. Sometimes we have a
No,
material which is,
sir.
yes please.
Yes, yes, sir.
Yeah, sometimes we have a material which is not having a not proper extrusion grade material, right? So
Okay.
for understanding whether my material is of extrusion grade or not, we used to study the MFI of that material. So this is,
MFI, right?
yeah,
Yeah. Melt
this
flow
is,
index, right?
yes,
Yeah.
this is as per ASTM 1238, right?
Okay.
So
Okay.
for most of the commercial printers that work in the range of 150 to 300 degrees Celsius, the MFI is
Send it to
normally
me.
acceptable
If
from
anybody will ask
250
after
grams per
that.
10 minutes, right? So if the
Yes, sir.
MFI is within this range, my material is considered to be acceptable for the some printing applications.
Okay.
Then, if you are really interested in some value-added product, we need to understand its thermal stability. So for
Okay.
thermal stability, for repeated heating cooling cycle, whether my material will be thermally stable, we used to study it on a DSC setup,
Okay.
right? Then if
Okay.
you are interested in adding some mechanical property to it, we
Right.
used to have a typical study on UTM for the peak length, peak elongation, peak strength, young modulus, modulus of toughness, these type of
Yeah.
the properties,
Yeah.
right?
Yeah. Yeah.
So
Yes, sir.
we can, depending on my application, I can think of thermal property, I can think of mechanical property, I can think of morphological property, right?
Yeah.
So
Yes, sir. Yes.
then, of course, there are surface property like in the form of hardness, porosity, surface roughness. This is also depending upon the application we see where
Okay.
we are going to use that.
Okay. Okay.
Right.
This is recording with filament wire, right? Yes, sir. Yeah.
Of course, the filament is going to, finally affect the property of the component. Huh? So,
Yeah.
if filament is not printable, the everything is lost,
Okay. Yes, sir.
right?
Yes, sir.
So,
Yeah.
the basic, we start with the flow
Okay.
property. That is the in terms, other terms, we call it as the rheological property of the material. So, first we have to establish the rheology of that material.
Yes, sir. Yes.
Right.
Thank you, sir. Thank you so much.
So, do we have any other?
Any other query from participant side? If anybody want to ask something related to this additive manufacturing? No more?
Mm.
I
Thank
think
you,
that
Dr. Mohit, for this opportunity. Yeah.
so we are very thankful to you. Thank you so much for delivering so nice talk on this. Thank you so much, sir.
Thank you
Thank
so
you.
much.
Thank you.
Dear participants, as per our schedule, the next session is to be delivered by Mr. Piyush D. UK. He is from Industry News Medicube Private Limited. As already he has delivered lecture on additive manufacturing hands-on training and applications. So within 5 minutes, or I think Piyush the UK is already joined. I'm right, Dr. Ravi?
Yes, he has already joined and we will start his first half of this session.
Yeah. Hello, sir.
Okay.
So, hello, Piyush, we will start at 11:30. So,
Yeah, we can start now, sir.
okay, we can start. Okay, just have this 1 minute only because there may be chances that in between the lectures, the participants are not present. Okay.
Okay.
Second, yeah. In 1 or 2 minutes later, so
Yeah, sure, no problem. I can we can wait for 1 or 2 minutes, or I'll be waiting for 4 minutes. So sharply at 11:30 we can start the lecture.
okay, no problem. No, within 1 or 2 minutes, we can.
Okay, sure.
Yeah.
So shall we start now?
Yeah, we can begin.
Yeah, sure, sir. So good morning, class. In the last session that we talked about the various open source software that we use for additive manufacturing, and we discussed about each and every steps. The first step was to generate a CAD model. So how we can generate a CAD model by using an open source software. In the next step, whenever we are converting the CAD model into an STL file, so it may happen then sometimes the errors are being generated. So how to rectify those errors, how to make sure that the file is error free, the STL is error free, that we have discussed by using the mesh mixture software. And later on in the third step, then we did the slicing operation. So we did the slicing operation on the open source software such as a Repeater host and Flash print. So that is all we discussed about discussed in the last session. So in the last session where we left was like we generated the G code, and that G code needs to be printed. So that is where we left the last class. So I'll be continuing the same. So today the main outline will be, wait, I'll be sharing my screen. So is my screen visible? Okay.
Yeah. Now it is easy.
Okay, sure, sir. So today's lecture will be mainly focused on hands-on training and application of 3D printing. So the main outline will be like I'll be giving you the demo of mesh mixture software again. Then I'll be giving you demo on FDM type of 3D printer, FDM or a triple F type of 3D printer. Later on, we will discuss about a DLP machine, like what is DLP machine, how it works, and then I'll be covering about some troubleshoots which we face while doing the FDM kind of 3D printings. Okay, so this will be the outline for today's lecture. First, I would like to tell you, like, are you aware of the Voronoi diagrams, Voronoi structures? But we all are aware with the Voronoi structures, but we don't know how to make such kind of structures, because these are the complicated kind of structures. And is it possible to make these kind of structures by using any kind of conventional techniques? Like, suppose I have these two figures are there, the left one and the right one. I want to manufacture these two models. So is it possible to manufacture this model by using any conventional manufacturing technique? Any answers?
No, sir. Oh, sir.
No, it is not possible to manufacture this kind of complex shape by using any conventional manufacturing technique. So if you want to make such kind of conventional, such kind of complex shapes or complex geometries, then additive manufacturing is the only option that we need to choose to manufacture them. Okay. So suppose if I want to manufacture this, the first step will be to generate a CAD model of such kind of Voronoi diagrams. So how we are going to make the CAD model for the same? So that I'll be teaching you now. So for that, what I'll do, I'll just open my mesh mixture software. Okay, so this is the software that we discussed last time. So the first step that I'll be doing is I'll be importing a CAD model. Okay, so suppose I have already generated a CAD model. Like, so today's exercise will be to make this kind of geometry. Okay, suppose if I want to make such kind of geometry, so the first step will be I need to have a STL file for the same. So I need to have a STL file of the sphere. So what I'll do is I'll open the FreeCAD software. I have opened the FreeCAD software. Now I'll be clicking on the start on this tab. From here we are going to make the part design. So I have chosen the part design. Then I'll be doing a create a new. We are supposed to make a new body on a sketch. So we are going to we are going to do a sketch on XY plane. Press OK. Okay, we got the sketch. Now the next step is to make the sphere. To make the sphere, I'll be making a semicircle. Okay. From the semicircle, I'll be drawing a line. Now I need to revolve this object, revolve this sketch along this axis. Okay. So I'll go to the model. I'll be selecting the sketch. I'll go to the task, and here we can see the revolve option. I want to revolve along the axis. I have chosen the axis. I want a revolution of. I want to revolve the body at an angle of 270 degree. Okay. So we got the model now. We got the model. Now I want to save the STL. So I have selected the body, and I'll be exporting this body as an STL file. I have exported the body as an STL file. Now what I'll do, I'll open the mesh mixture. I'll import the STL file. Now I want to import the STL file that we have just saved. So this is the STL file that we have exported. So I'll be importing this STL file. So this is the model that we got. Now I want to make the Voronoi diagram. So in order to make the Voronoi diagram, what I need to do, I need to remesh the geometry. So I'll be selecting, I'll be pressing the select tab and I'll be double clicking the entire body. So entire body has been selected here. And I'll be go to the edit, remesh. In the remesh tab, I'm doing the adaptive kind of meshing and I'm controlling the density. So by controlling the density, we can control the mesh size. So suppose this is the geometry that, this is the mesh that I have selected. So what I'll do next, I'll be clicking on the edit. From the in the edit tab, we will find the make pattern option. So I'll be clicking on the make pattern option. In the make pattern option, we can see that these are the type of patterns that those are there. Like this is the tile tube type, and there are a number of other options are available. So I'll be choosing the dual edges. In the dual edges, can you see the structure has been changed? So from here we can control the element. From here we can control the element size. Like what should be the element size? Like I want a thick element. So I'll be having a element size of 3 mm, or if I want to have a thin kind of structure, so I can have element size of 1 mm. So likewise, I can control the element size. I can control the element spacing from here. So what it will do is it will try to connect all the vertices. So whatever the vertices are there, it will try to connect those vertices with the element type, with the hexagonal grid type. So that's why we did the remeshing thing. Like suppose if the mesh is too fine, so maximum there will be more number of nodes are there. So this kind of geometry or this kind of hexagonal grid is going to be more refined, or more smaller grid is going to be there. So it will increase the computational time. So in order to reduce the computational time, I have increased the mesh size. I have reduced the mesh size and I made it a coarse mesh. Now the next thing is I'll be pressing the update key. So it will start generating the Voronoi structure. It is going to take some time. It will take around 5 to 10 minutes to generate the model. So in the meanwhile, what I can do is we can move further. We will allow the software to perform the operation and we can move further. And once the model has been generated, then I'll be showing it to you that how the model looks like. So this was all about the Voronoi diagram that I wanted to show it to you. Okay. So the next thing is like we discussed everything about the we had a theoretical lecture about the triple F kind of 3D printing. We know the basic working of the triple F kind of 3D printing. Now I'll be just giving you the demo how the printer looks like. Where are all the components mounted, and how we are going to perform the operations on the 3D printer. Yeah, just give me 2 minutes. Is it visible now? I think now it's okay. So this is the Dr. Ravi, am I audible to you?
Sir.
Okay. So this is a FlashForge Creator Pro 3D printer that we have in our office. So this printer is having a build volume of, in X direction it has a build volume of 210 mm. In Y it has a build volume of 150 mm, and in Z it has a build volume of again 150 mm. So that is the build volume the FlashForge Creator Pro printer allows me. And this system is a dual extruder nozzle system. So that's the extruder. So here we have two extruders, two nozzle system is there. So the right nozzle or the left or the second extruder, we can use it for let's say we can use to print the support material, or dual extrusion also allow us to do the dual material printing, or we can do the multi material printing. And this is the bed. This is the bed that we have, and the bed will move in X and Y in Z direction, and the nozzle, the extruder head will move in X and Y direction. I'll be showing. So the extruder head will move in X and Y direction. So this is the geometry. This is the basic working structure of the 3D developed kind of 3D printer. So if you want to start the 3D printer, what will be the first step? The first step is to load the material. Okay, so I'll be needing to load the material. So here we use the filament in the we use the material in the form of a filament or wire. So what I'll be doing is I'll be loading the material from this end. So this is the point from where we just enter the material. So what I'll be doing is I'll be loading one material. So now I got the ABS material. So this is the filament that I'm going to load. So we will be loading the material on the right hand side extruder. So in order to load the material, what I'll be doing is now the screen is visible. So I'll be going to the utility. In the utility, first of all, I need to preheat the machine. So I'll be clicking on the preheat. So I'm supposed to load the material on the right hand side. So I have chosen the right extruder as on, and I'm doing the start preheating. So can you see here the temperature that I have set is 240 degree and the current temperature is 35 degree. So the machine have started preheating. So we need to wait till the machine preheats. Is it possible to load the material in the normal room temperature, or without preheating? Can we load the temperature? Now the system has been preheating. We reach the temperature of 180 degree. So the machine has been preheated now. So now what I'll be doing is I need to load the material. So in order to load the material, I'll again press back. So here from the left key we can press the back side. So now I'm pressing the down key and I'm selecting the utility. In the utility, we can see the second option as a filament loading. So in the filament loading, I am supposed to load the right extruder. So I have chosen the right extruder, load right, and we can see here the message has been flashed, begin loading. So now we need to load the material. So in order to load the material, what I'll be doing is, this is the filament that I wanted to load. So I'll be inserting the filament into the opening of the extruder. And from here, from the right hand side, the material should come out. We can see the material has been coming out. So it has successfully loaded the material. Okay. So now we have loaded the material. What will be the next step? So the next step is we need to do the bed leveling. So now I'm supposed to level the bed. So in order to level the bed, I'll be again going to the utility tab. So I'll be pressing the left key. I have pressed the left key. Now I'm moving downwards. From here we can see the build level plate option is there. So I'm choosing the build level plate and I'm pressing the OK button. Now we can see the extruder is been moving to the home position and the bed is also moving to the home position. Okay. Now the extruder and bed have moved to the origin, to the exactly center. The extruder have moved to the center and the bed is at the home position. Now we need to do the bed leveling. In order to do the bed leveling, so in order to move the bed leveling, what I will be doing is, can you see this screw? This is the bed leveling screw on the front side of the bed. Likewise, we do have two more screws which are at the farthest corner. So this is the second screw. Likewise, there will be another screw. So two screw will be on the front side, two screw will be on the back side. So I just need to unscrew or tighten the screw or loosen the screw in order to maintain the distance between the bed and the nozzle. So to do the proper kind of bed leveling, I'll be using a piece of a paper, okay, and I'll be manually moving the extruder head to this front side. Okay. So what I'll be doing is I'll be placing the paper in between the nozzle and the bed. So this is the paper that we have placed, and I'll be loosening the screw. Once I start loosening the screw, this paper, the distance between the nozzle and the bed will decrease, and the paper, now the paper is too loose and we can easily pull out the paper. So once we loosen the screw, the tension between the paper and the nozzle will increase, and it will be slightly difficult for us to move or pull the paper. So I need to just loosen the screw so that the paper cannot be pulled out easily. Now I have again loosened the screw, and we can see now the paper is slightly tight between the nozzle and the bed. So this much is the distance that we need to keep. Now we have leveled the front side. Now I again need to level on the back end side. So I'll be moving this printer. I'll be moving the nozzle to the extreme back corner of the screw. I'll be again doing the same procedure. Okay, I have inserted the piece of paper here. Now I am loosening the screw, and I'll try to pull out the paper. Okay. So now the paper is slightly tight. So this much distance is okay. Now I'll be moving the extruder head to the right hand side. I move the nozzle to the right side. I have again inserted the piece of a paper here, and I'm loosening the screw. Okay, it's done. Okay. So now what we did is we had done the bed leveling. Now the bed is properly been leveled. Now the next step will be we just need to load the material. We have already loaded the material. We have already leveled the bed. Now we need to start the print. In order to start the print, this is where the memory card has been inserted. This is the SD card that we're using to print the model. So I'll be just keeping this SD card inside. I have already made the G codes, and we have already installed the G code within the machine. So I'll be doing is I'll be inserting this SD card here, and I'll be selecting the which file to be print. So in order to select the file to be print, what I'll do is we can see here the option is there, print from SD card. So I'll be choosing the print from SD card option. I'll be pressing OK. Now we can see here all the G codes are being loaded. So I just need to select what kind of material I want to print, like which model I want to print. So suppose I'm choosing this. Suppose I'm choosing this packing cover to be printed. Now I'll be pressing OK. Now we can see here the extruder nozzle have moved to the extremely left hand corner. So it is the zero position for the nozzle to park, or it is the parking position for the nozzle. And the bed have also moved to the initial position from where the print will start. So it will again wait till the machine preheats. Now the machine has been preheating. And we can see here the platform temperature is rising to 90 degree, and the extruder temperature is rising to 240 degree. So the machine will preheat, and once the machine will preheat, the print will start. Okay. So this is about the FDM kind of 3D printer. And do you have any doubts regarding the same? The part that we are printing is going to take around 3 to 4 hours. So it's a quite big part. So it won't be possible to show you the entire printing structure. So what I'll do is I have made some videos. So I'll be showing you the video of printing, like how exactly the machine behaves, how the machine is going to print the model. So till the time, do you have any doubts in the machine, like in the operation or anything? If no doubts, then we can proceed further. So this was all about the demo of FDM kind of FDM or triple F kind of 3D printers. So I'll show you again the DLP kind of 3D printing machine that we have. Yeah, hello. So we have seen the triple F kind of 3D printing machine. Now I'll be showing you the DLP kind of 3D printing machine. So are you aware of the DLP kind of 3D printers?
No, sir.
Okay, and SLA? I'm sharing my screen now. So this is how the machine is going to print the part. That's the extruder head, which is moving in X and Y direction, and the bed will move in Z direction once the layer has been completed. And this one is the finder machine that we have. And we can see as we pulled out the filament, we pulled out the spool. So it will give us an error that the filament is not been detected. It has automatic filament detection sensors. So it will flash the error as a filament error. Now I again need to load the filament, and I'll be making sure that the filament is properly loaded. Once I made sure that the filament is properly loaded, so it will again start printing the material. It will again start printing the model. So it will resume. It will resume from whatever position it has stopped last time. So it will resume from the same point, from the same position. And this is the final part that is going to be printed. Okay, so is it clear? So shall we proceed with the DLP kind of 3D printing? Okay. Yeah. Just give me a minute. I'll make sure the machine has been ready. So this is the DLP machine that we have, and this is the post curing unit along with the DLP machine. So cover निकालो ऊपर का. So here can you see that this is the bed, this is the print bed, and the bed will move in Z direction, and the projector is there which is inside the inside this VAT. So suppose I'll be pressing to the tools. From the tool I'll be moving the Z axis, and I can select like by what I want to move the Z axis as 0.1, 1 mm or 10 mm. So I'm choosing a distance of 10 mm, and I'm pressing the up key. So can you see the bed is been moving in up and down direction? I have pressed the home key, so it is going to the home position. Okay. Now I'll be again doing the same thing. What I'll do, I'll make sure I'll be moving the bed in up direction. Okay, so this is the VAT tray that we have, and this machine is having a build volume of 200 mm in X direction and 150 mm in Y direction, and in Z direction the distance is 245 mm. So that is the build volume that the machine is that the machine is providing us. And here we can see the gray resin has been inserted. So this is the gray resin that we are using. So that's a VAT material, and this tray is known as a VAT tray, where we are going to place the material. Now once we loaded the material, what I'll be doing is I'll be doing the same operation. I have made sure that I have the sliced model. So that slice model has been inserted from the pen drive, from the USB drive to the machine. So I'll be choosing, like, I'll be going to the home. From here we can see the first option is a print option. In the print option, I can see the various kind of models are been loaded. Various kind of model are been loaded. So I just need to choose a proper kind of model that I want to print. Suppose I want to print this castle. So I have chosen this model. Now I need to press the print option. So what I'll be doing is I'll be removing the bed, and I'll be showing you how the layers are being projected on the screen. So for that I need to remove the bed. So to remove the bed, these are the screws, unmounting screws. I'll be just unscrewing them. And we have removed the bed. We have removed the VAT. So what we will be doing is, I have already selected this model that I want to print. Now I'll be pressing the start button. So we have started a printer. Now this is the screen where the image has been projected. Now so it will move till the bed reaches to the home position. We have also removed the bed so that the projection can be seen quite easily. So first the bed will move to the home position. Okay, the bed have reached its home position. Now the first layer will start. Can you see here the UV light, the purple light has been flashed, and in between there is a white color cube. There's a white color square. So that square is the first layer that we are printing. So those are the projection of the layer that we want to print. and the remaining UV light that we can see here is the total build-up area or the total projection area. So in the from the total projection area, we are only printing in the center with a small kind of area. So that small area has been highlighted has been highlighted properly, and only the material which is present there on the center, it will be cured. So this is a photo curable material. So the material will be cured by using the UV intensity UV light. So once the first layer has been completed, so the bed will move in up direction, the bed will move in Z direction, it will move upward, and it will allow the fresh resin to move between the bed and the vat layer and the vat tray. So fresh material will be there, and that fresh material will be again cured by using this kind of UV lights. Now the second layer will be printing. Now second layer is completed. So the bed is moving in the Z direction upward. It will again move downward. And the third layer have projected. So like whenever the one layer has been completed, so what the bed will do, the bed will move up, the bed will move upward first, then it will again move downward. So it will make sure that it has this kind of up and down movement, so that whatever the material which has been which is stick between the vat film and the bed, that material needs to be removed properly. So that's why the bed will move in up and down direction. So once the bed will move in up and down direction, so the model has been removed properly from the resin, from the film, and the fresh resin will come in between them, and it will again do the successive layers. So this is all about the DLP kind of 3D printing machine. And once the model has been printed, so what we do is, the model is printed. So this is the post curing machine that we have. So what we will be doing is, we do have, so So what we are going to do is, like, we need to clean the material. So it's a UV curing resin. So we need to wash it out the resin. So in order to wash the resin, we do have some containers with us, and isopropyl alcohol has been used to wash the material. So I'll be placing the tank here. I'll be placing the tank on this top, and we will start the stirring operation. We will start the washing operation. Okay. So I have placed the bed. Now what I'll be choosing is, I'll be pressing this tab, and I'll be choosing whether I want to do a curing or washing operation. Suppose I want to do the wash operation, and from here I can choose how many minutes I want to wash the material. So I've chosen as a 2 minutes, and I'm pressing OK. So we can see here the nozzle have started moving, the fan has started moving, and it will give a swirling effect there within the resin or within the isopropyl alcohol that we're using to wash. And a turbulence will be created there, and because of the turbulence, the whatever the model which has been kept inside this tank within the isopropyl alcohol, so it will be cleaned properly. So this is how we do the post curing operation. And if you want to do a post curing operation, like suppose we want to do the post cure by using UV light, so that option is also there. So in order to do the post curing, so what I'll be doing is, I'll be pressing this button. I'll be selecting the cure option. Again, I'll be selecting the time by which I want to cure the material. I will insert this plate here. We are going to keep any kind of random model. Okay, suppose this is a model that I wanted to cure. this is a model that I wanted to cure. So now I'll again press the OK button. So it is flashing me a beep. It means that it needs a UV protection cover so that our eyes are being protected. So we need to place this outer cover. Once we place the outer cover, we can see the UV light has been started and the material will be post cured. Okay. So this is how we can do the post curing operation in the DLP machine. Okay. So it will be cured for another 1.5 minutes. And once the machine is once the time has been completed, so it will flash a beep and it will let us know that the curing has been completed. So we can remove the material and we can do the post processing or any other finishing operation that we want to do on the model. So that we can do later. So this is all about the DLP kind of machines that we have. Currently, we have two DLP machines with us and two FDM kind of machines with us, and we're using the DLP machine to make the industrial parts, and we're using the FDM machine to make the anatomical models that we are making, that we are manufacturing. So this is all about the demo of the DLP and the FDM kind of machines that I was supposed to tell you. Any doubts till now?
Hello, sir. Yeah. What is the main difference between SLA and TLP type machine, sir?
In SLA kind of 3D printing, we do use a laser, and in DLP we are using a projector there. So while when we are using the SLA kind of machines, there is a laser and it will cure the material from a spot, like as we do in the FDM kind of 3D printing machine where we have a nozzle. So that nozzle is going to follow the entire path. Okay. But in DLP, as I have shown you here, so the entire layer can be projected in a single go. Like suppose if I want to make a cube, and we are making a cube by using SLA. So what it will do, it will first make sure that the contour has been printed properly. So the laser will move in the contour direction, and once the laser moves in the contour direction, then it will start making the infills, as we do in the FDM. And whereas in DLP, if I want to make a cube, so it will going to project the entire layer of the cube on the printer bed, and the entire layer can be cured within the same time.
Okay, sir. Thank you.
Any other questions? Yeah. So this was all about the DLP and the FDM printer that I was talking about. So I'll again show you one video of the DLP. Is my screen visible to you all now?
Yes, sir.
Yeah. So this is how we are inserting the bed, and now we are pouring the resin in the vat tray. So this is the Voronoi model that we are supposed to print by using the DLP machine. So they are slicing the model. Now they have chosen the part to be printed. Now the print has been started, so bed will move in Z direction. It will move to the home position. Once it moves to the home position, the material will be start printing. Can you observe that the bed is moving continuously in up and down direction? So this is how the model is going to be printed in DLP. So which technique is will be faster, DLP or FDM? Now we need to remove the residual resin. Now they have cleaned the model in the isopropyl alcohol. So it will remove the whatever the residual resin is there on the model. So it will remove all those resin, and we can make such kind of complicated shapes by using DLP. So DLP is having a more accuracy as compared to the FDM kind of 3D printing. Here we can achieve an accuracy of up to 35 microns in Z direction, whereas the FDM, it is having a limitation of up to 100 micron in Z direction. And the XY resolution we can in DLP we are printing it by projecting the entire layer on the screen. So there the screen is having the pixels, so each and every pixel will control the X and Y resolution. So one pixel is having a dimension of 47 micron. That means minimum to minimum at least 47 micron should be printed on the DLP machines. I never tried to print anything up to anything of 47 micron size, but you can definitely try to print any object which is having a size of 47 micron. That is the size of a pixel. So at least that much amount of pixel the DLP machine is going to lighten up on the screen. So you can check if you are able to print 47 microns of model or not by using the DLP machines. Whereas the FDM, in FDM, we are using a nozzle of 0.4 mm, which will be around 400 microns. So whatever the one drop or the one point that we are going to print, or one drop that we are going to print by using FDM, so it will having a diameter of 400 microns. So the minimum XY resolution for the printer is going to be the 400 micron, the layer width. Whereas the same layer width that I am talking about in DLP is 47 micron, that is the 1 pixel size. So you can imagine like what kind of accuracy dimensional accuracy we can have while printing it with SLA or DLP kind of machine as compared to the FDM kind of machines. So this was all about the FDM and DLP demo. Now, if you have any doubts, so you can ask me, or we can proceed further with the troubleshoots of FFF kind of 3D printing techniques. So let's proceed further then. So the common problem with the FDM kind of 3D printers are, the first problem is the under extrusion is going to be there, over extrusion is going to be there, holes and gaps on the top layer can be there, stringing or oozing can be there, overheating problem is there, layer shifting or misalignment, layer separation or splitting, filament grinding, clogged extruder, curling or rough corners, scars on the top surface, gaps in the thin walls, inconsistent extrusion, warpage. These are some of the problems that we are going to face every now and then whenever we are doing the FDM kind of 3D printing, whenever we are operating the FDM 3D printers. So it is not like we are going to face the all of this problem at a single stretch, but any of one of the problem we can face whenever we are doing the printing. We can encounter any problems. Okay, so let's discuss about these problems in details. So if we talk about the under extrusion, the first problem is of under extrusion. So this usually have when the material is not been properly extruded, or the feed rate and the flow rate are not properly managed. So in that time, the under extrusion is going to be there. Like here we can see the gaps are been we can observe the gaps on the top layer. Like suppose this was the material that we are supposed to print. From here we can see this layer width is properly. So we need to have a material like this, but we are getting a material like this. The waviness or the somewhere the inconsistent material extrusion is there. So this kind of inconsistent extrusion will be happening if the nozzle is blocked. Like suppose if the nozzle is not clear properly, so then the material won't be extruded properly. So at that time we can see the under extrusion problem. Or if the material is not, if the feed rate and flow rate is not matched properly, then also we can see such kind of problem. So if you want to avoid this kind of problem, so what we can do is, or else this problem can also be happened if the filament diameter is incorrect, if the filament diameter is not consistent, then also we can observe such kind of problem. So if you want to avoid this kind of problem, so what we can do is we can increase the extrusion multiplier, we can increase the flow rate and feed rate, we can clear the nozzle, and we can clear the throat as well. And we can check if the filament is having a consistent diameter or not. If we replace the filament with a consistent diameter filament of 1.75 mm, then we can avoid the under extrusion problem. So this is the most common problem that happens usually while doing the FDM printer. The second problem is over extrusion. So here we can see the material has been overheated, and due to the overheating, the material has been melted. The material has been melted too much, and it has not been able to manage its shape. So this usually happens if we are doing the excessive kind of heating on the material, or if the cooling is not sufficient. So if you want to avoid this over extrusion kind of problem, so we need to set a proper kind of extruding temperature, and make sure that the cooling is proper, make sure that the cooling fan is properly operated, and the material as well as the extruder fan that will cool the extruder motor and the extruder assembly before the throat or the nozzle. So that extruder fan should also be working properly. If the cooling fan and extruder fan are working properly and the material temperature is okay, so then we can avoid the over extrusion kind of condition. The next thing is holes and gaps on the top layer. So this thing can be happened is, suppose if we are making a geometry by using infill pattern or use infill density. We are controlling the geometry by using infills. Suppose I am printing it with 30% infill or 20% infill. In that case, what can happen is the inside structure is porous, and if we don't have the sufficient number of top layers on bottom layer, so there we can see this kind of gaps on the top layer. So here, if we increase the number of top layers, like here, this model is having only one top layer. So instead of having one top layer, if we increase the top layer to 2 to 3, then we can avoid such kind of holes or gap on the top layers. Okay, and it can usually happens if the number of top solid layers are not okay. Like as I've told you, like here we are having only one layer instead of having 3 layers. If the infill percentage is also too low, then such kind of problem can happen. And even if the condition is of under extrusion, like the nozzle is blocked, or the nozzle is blocked, or we can say the flow rate or feed rate is not matched properly, then also we can have such kind of problems. Okay. So the next problem is the stringing or oozing. So here you can see the threads are being pulled out from the model. Like this stringing and oozing will usually happen when the printer is moving from no print zone. Like suppose if I just check this particular layer, so what will happen? The nozzle will move from this point to this point, During this movement, the material should be extruded from this particular point to this particular point. The material should not be extruded. From here again the material extrusion will start up to this point. Again the material extrusion will stop up to this point, and then the material will extrude up to this layer, this side. Okay, so this is the print zone. Print speed. Here is the print zone. This is the travel speed or no print zone. So here the speed that will govern is the print speed. Here the travel speed is going to be governed. Again the print speed, the travel speed, and print speed. Okay, so this is how the model, the printer will work. And during this no print zone, suppose if we increase the travel speed, so increasing the travel speed, what will happen is it will whatever the material that it has deposited the last time, so it will try to stretch the material. It will try to stretch the material or pull the material. So while stretching or pulling the material, such kind of small threads can be formed. Okay, so these threads are known as a stringing or oozing. So if you want to avoid this stringing and oozing, what we can do is we can increase the retraction distance, or we can increase the retraction speed, or it can happen if the print temperature is too high, or if this no print zone or no print distance is too long. Like here we can see the no print distance is too long. So here also the stringing and oozing can be we can observe the stringing and oozing. Are you aware of the retraction speed or retraction distance? Like the retraction speed is what? Suppose this is my bed and this is my nozzle that I am printing. Okay, so whenever the material will, whenever we are moving towards from print zone to no print zone, what the machine will try to do? The machine will try to pull back the filament. So it will pull back the filament so that the material is not been extruded due to gravity or due to overheating or whatever. The material is already be converted into a molten form. So due to gravity, the material can be extruded. So to avoid the extrusion, we are just pulling back the filament. So that pulling back of filament is known as a retraction. So by how much distance the filament has been pulled, it is known as a retraction distance, and by what speed the filament has been pulled back is known as the retraction speed. So if we have a proper or optimized kind of retraction distance and retraction speed, so we can avoid the stringing or oozing kind of problems. Again, the next problem is of overheating. Like whenever we are printing such kind of this kind of model, like the geometry is too small. Like suppose here I am printing we are supposed to print a pyramid. So in the pyramid, the apex side, the area is too small. So how the nozzle, suppose if I am printing on the base, so the nozzle will move like this. It has a maximum area, too long area. So this is the first point where I have extruded the material. So my nozzle will move like this, and it will come back to the first point till the nozzle reach back to the first point. So the material which was extruded for the first time, it got sufficient time to cool down. But as we reduce the distance, the time the material gets to cool down will be reduced. So it is not going to have a sufficient time so that the material is cooled down. That's why here we can observe, like on the base side, we do not have any kind of overheating problem, but as we reach towards the apex, we can see the overheating problem is there. So if we want to avoid such an overheating problem, what we can do is either we can make sure, like we can make sure the printer head will pause for 1 or 2 seconds before printing this top layer so that the material will get sufficient time to cool down, or we can increase the cooling speed or cooling fan speed. So, and we can reduce the print speed as well. So all these remedies that we're using, it will reduce the overheating problem. Okay. So the next problem is layer shifting and misalignment. So in the layer shifting or misalignment, we can see this entire layer has been shifted. So it has shifted its contour, and here we can see the internal infill has been printed by 20 or 30%. So this problem usually happens when the print head is moving too fast, or it is having any kind of mechanical or electrical issue. Like if there is a fluctuation, if there is light fluctuation, so due to the light fluctuation, this problem can happen. Or if the printer head is moving too fast, so the belt will jump from the gear. So if even if the belt jumps from the gear, if it skips one tooth, then we can observe a misalignment of more than 2 to 3 mm. Okay, so that's why the printer head should move quite slowly. It should not move beyond its speed. And we should always avoid the mechanical or electrical issues, like the proper stabilized voltage should be given to the machine. And we need to make sure that the belt is properly tight. The belt is not too tight, not too loose. If the belt is optimally tight, then we can avoid the layer shifting or misalignment problems. Okay, so the next problem is the layer shifting, layer separation or splitting. So this is the problem which we usually have when we do not have a proper kind of heating arrangement, or when the print temperature is not sufficient. Suppose if we are printing it at a very low temperature, then the material won't get stick to the previous layer. Like for example, like if I want to print the ABS material, and the print temperature of the ABS material will be around 240 degree, like 230 to 250 degrees the print temperature of ABS material. And if I'm printing the ABS material with a print temperature of 210 or 220 degree, so in that case what will happen, the beneath layer will not be heated properly, so that the topmost layer or the successive layer can be sticked on the previous layer. So if that condition happens, then we can see the layer separation or splitting we can observe the layer separation or splitting. Okay. So the next problem is the filament grinding. So filament grinding usually happens when the nozzle has been clogged. If the nozzle is clogged, so the filament, the material won't be able to push to move out from the nozzle or to extrude it out from the nozzle. So the material, the filament will be stuck at one particular end, and the roller will continuously moved. So that roller, what will the roller do? It will grind the material. So this is where the roller is continuously moving at one particular point, and this is the point where the material has been clogged or the material has been blocked, and due to which the filament has been grind. So if you want to avoid filament grinding kind of problem, so what we need to do is we need to make sure that nozzle is cleaned properly. We are not printing at a very high speed, and we can, even if the nozzle has been blocked, if we slightly increase the temperature, so sometimes it happens that the blocked material is moved out from the nozzle exit, or it has been extruded from the nozzle. So if you want to avoid the nozzle blocking kind of problem, so one thing we can do is we can increase the print temperature, and we can increase the print temperature. We can wait for 5 to 10 minutes at a higher temperature. Whatever the material which is there, which is blocked in the nozzle, it will melt it down. Then we can again load the filament. So whenever we load the filament, it will push the clogged material from the nozzle to get extruded from the nozzle. Okay. So next problem is the clogged nozzle or the clogged extruder. So in the clogged extruder, if the nozzle has been blocked, like I told you that we can manually push the extruder, we can increase the temperature, and we can wait for 5-10 minutes, and then we can again load and push the material to come out from the extruder. Or second thing is we can do the reloading kind of filament. We can just unload and reload the filament 2 to 3 times. So sometimes it happens that it also removes the blockage in the nozzle, or even if by using these 2 remedies the nozzle blockage has not been removed, so what we will do is we will just remove this nozzle, and once the nozzle is removed, we can see the material has been blocked here. So we can dip the nozzle into the alcohol or into any kind of dissolvable material which can dissolve this inside plastic. Like suppose if we are printing it by using a ABS material, so we can dip the nozzle in the acetone. So what acetone will do, acetone will dissolve the ABS material, and it will just flush out all the material from the nozzle. So now after like we can dip the nozzle for 2 to 3 hours or more than 6 hours, depending on what kind of blockage is there. So after that time, we can observe that the entire plastic has been removed out. It has been melted, dissolved in the acetone. It has moved out from the nozzle. Then we will get the cleaned nozzle, and we can use that clean nozzle for further printing. Likewise, we can clean the nozzles. And the next problem is the curling or rough corners. Like here we can observe the rough corners are been curled. So this curling is usually happen if the print temperature is too high. So if we do not have a proper kind of cooling arrangement, so if we are printing it with optimized kind of optimized kind of print temperature, so we can avoid this kind of curling or cooling corners. Okay. And the next problem is the scar on the top surface. Here we can see like we are getting a nozzle marks on the top surface. Like many times these kind of marks have been observed on the print part. If such kind of marks have been observed on the print part, it means that we are extruding too much of material. So we are doing the over extrusion kind of thing. So in order to avoid this, what we will do is we will reduce the we will try to control the feed rate and the flow rate. If the feed rate and flow rate are properly controlled, so we can avoid this kind of problem. Next problem is the gaps in the thin walls. We can observe such kind of gaps in the thin walls are there. So why these gaps are being observed, or why these gaps will be there in the print? Like this will happen. Like suppose if we do not have a sufficient kind of thickness, wall thickness, so then we can observe such kind of gaps. Like we are printing it by using a nozzle of 0.4 mm. Okay. So what will happen is, this is the first layer. The layer bit is 0.4 mm, and suppose I do have a thickness of 1 mm. So what will happen is, this is the first contour of 0.4 mm. This is the second contour of 0.4 mm. Okay. So the sum of two contour will be 0.8 mm. The remaining is 0.2 mm, and we are printing it with the 0.4 mm. So whatever the gap or whatever the distance, remaining distance, which is less than the nozzle diameter, so it will skip filling that part. But even if we increase the same wall thickness to 1.2 mm, so then we can avoid such kind of gaps. Like what it will do is, it will make that the 0.4 mm the first contour, it will make the 0.4 mm second contour, and it will make the 0.4 mm of third contour. So we can have a wall thickness of 1.2 mm properly. So always try to make sure that whatever the minimum layer, minimum wall thickness that you are trying to print, it should be a multiple of your nozzle diameter. If it is a multiple of your nozzle diameter, then such kind of gaps can be avoided. Or the thumb rule that I use during my designing time is, I always make sure that I do have a minimum wall thickness of 1.5 mm. If I have a minimum wall thickness of 1.5 mm, so usually such kind of gaps are avoided. And if you want to print such kind of small features in FDM kind of 3D printing machine, so this like here we can see in the CAD model, from left hand side to the right hand side, we are reducing the thickness. Okay, like in the CAD model we can see this is the thinnest model that we want to print, but it has not printed the entire model. Like the last three models are skipped. Okay, why this happened is, as I've told you, that whatever the feature is there which is less than the nozzle diameter, so it will try to skip that model. So the slicing will not be generated, or the tool path will not be generated for the same. So if you want to print a minimum feature, make sure that the minimum feature is the multiple of your nozzle diameter. Like suppose if this minimum feature was of 0.4 mm, so it might have happened that it would have had printed a single layer or a single contour. And the next problem is the inconsistent extrusion. So inconsistent extrusion usually happens if the filament has been tangled, or if the filament has been locked within the spool, or if we have a blocked kind of nozzle. If you are printing it at a very low temperature, that at the time also the inconsistent extrusion can be there. And if the filament quality is not good, so then also we can have a inconsistent extrusion. Or if the extruder assembly is blocked, or if the extruder gears are blocked, so the extruder gear won't be able to maintain the sufficient pressure to pull the filament into the extruder nozzle. So in that time also we can have an inconsistent extrusion. So if you want to avoid this inconsistent extrusion, what we can do is, we can just check if the extruder gear, if we need to make sure that the extruder gear are working properly, the gears are clean, the filament quality is good, and we are printing it at a very good temperature, at an optimized temperature. If we have all these problems, if we are make sure that we do we are cross-checking all these things, so inconsistent extrusion can be avoided. And the last problem is the warpage. So such kind of problem usually happens when we do not have a sufficient, when the warpage happen when we are not hitting the bed properly. So the bed should be heated properly, and the bed adhesion should be good. And to improve the bed adhesion, what we can do is, we can add a brim and raft within the bed. So if we add a brim and raft, we can avoid the warpage. And if we maintain the bed temperature close to the glass transient temperature of the material, then also the warpage can be reduced. Okay. So these are some of the problems that we faced while doing the FDM 3D printing. So this was all about that. I wanted to tell you about the demonstration today and the application side. Now, if you have any doubt, so you can ask me.
Yes, sir. Yeah.
Yeah.
Hello.
Hello.
These are the
Yes.
troubles, sir. While printing, we may observe after printed, the components are verified, sir. Okay. Sir, in order to online monitoring, how we are going to supposed to do, sir? Because the once the product is printed, it may be the some damages, some troubles means it is wasted one, right? In
Yeah.
order to avoid that, how we are control or monitoring the performance of oil printing itself by using some sensors like this. How we are going to adapt these things, some
Like
changes.
the machines that nowadays the machines are coming with few of them, few of the sensors. Like once a sensor is there for filament detection. Like suppose if while printing, if the filament is empty or the filament is completely used, or the filament has been broken. So in that time, what can happen is the material, the machine will sense whether the filament has been properly coming or not in the inside of the extruder. If it senses that the filament is not coming properly, so it will pause the machine and it will flash an error. So then the user needs to go to the machine and he needs to check whether the spool is empty or whether he or she needs to replace the spool. And if all this problem, if they replace the spool and they again reload the material, so the machine will start again from the same point. And the second monitoring thing that we can do is we can have an camera option there, so we can observe like whatever the part has been printed. If we see that suppose if there is any kind of trouble is there, or the part is not been printed properly, or after some times if the part has been removed from the bed and we are not extruding the part properly on the bed, or the print fails, so we can remotely just switch off the machine by using any kind of IoT tools. If we have connected a machine with the Wi-Fi system, so we can
Okay.
remotely access the machine and we can switch it off the machine from anytime, anywhere. But for that, you need to have a Wi-Fi module within the machine, and you need to have a camera installed in the machine so you can observe the prints.
Okay. Okay. Another question, sir. How we
Yeah.
can relate the surface quality with respect to this troubleshooting or maintenance of this printer?
Like
How much it affects the surface quality, sir? Yeah.
if you have calibrated the printer very well, if you have calibrated the printer properly, so then we can improve the surface quality. If you want to improve the surface quality, it depends on the parameter by which, like it is a dual kind of approach. So it depends on the parameter by which you are printing you're printing the model. Suppose if you like if your machine is properly calibrated and you are not using optimized kind of parameter which needs to be there for printing that material or that model, so then also the surface quality is going to be reduced. And if we are using optimized kind of parameter which are recommended to print the model, or the material, and you
Okay.
have not calibrated the machine properly, so then
Okay.
also the surface quality is going to be reduced. You
Thanks.
need to make sure that
Yeah, yeah.
both the things are properly optimized.
Yes, sir. Thank you, sir. Thank you, sir.
Yeah. And another thing we can do with the FDM kind of machine is we can in the last class, the sir was telling about the composite filaments. So if you have the composite filaments and if you know the parameters, so you can use those composite filaments to print the material by using FDM kind of machines.
Okay, okay, sir. Okay, sir. Okay. Thank you.
Yeah. So any other questions? Have you understood or not the working of FDM and DLP machines?
Yes, sir. Yes, sir. We understand, sir. from your video explanation. We understand the things, right?
Okay, Dr. Ravi, I think no more questions are there. If no more questions are there, so shall we stop now? Yeah,
Hello.
yeah,
Sir, as you are dealing with these all machines, sir.
yeah.
Sir, with these machines, what are the parts products you are printing, sir, for outside applications?
Like we are making the anatomical models by using this kind of machines, and we are also making the few we are serving few industries to for making the customized packaging solutions for them. Like there are few industries who are working for the aerospace who are working for the aerospace industries. So they do make the dedicated models, and they supply those dedicated model to the various kind of space agencies across India or across the globe. So while transporting it happens like those all those dedicated components get damaged. So what we do is we do provide them a smart and effective way of packaging solutions, and all those packaging solutions are customized according to the product that they are manufacturing. And those packaging solutions are been printed, and we supply those packaging solutions to them, so that the product can be packed very safely within a strong and sturdy plastic kind of object, and it can be shipped or transported quite easily and without any kind of damage. So we are serving them, and we are serving the medical industries. So we are using this kind of technology to develop the medical devices, as well as to prove the for the initial validation of the medical devices, as well as we're also using the technology to make the anatomical model, as I've mentioned to you, and we are making those anatomical models available to the medical institutes for teaching and learning purposes. And we do also make the pre-surgical models which can be used by regarding the 3D printing. Okay. So thank you all for the opportunity, like for giving us the opportunity to demonstrate you about the 3D printing technology that we're using. And thank you.
Thank you, sir.
Yeah.
So, dear participants, so it was the second technical session of this fourth day of this FTP is already over. So you can take your time and have lunch. So we will meet at the last session of today, sharp at 2:30. Okay, so that will be our post lunch session. Okay.
A very good afternoon to everyone. So I welcome you all in the post-lunch session. So tomorrow we have two sessions after lunch. One session I am going to take on the direct parrot processing, and second session will be on the 3D medical imaging. Okay, so that lecture will be taken by one of the industry expert. Okay, so we will start this session very soon because only 30 participants have joined so far. So let's wait for a few minutes, then we will start. Okay, so please tell me if my screen is visible to you.
Yes, yes, yes.
Thank you. So dear participants, the topic of today session is the direct palette printing, scope, challenges, and case studies. So first I will tell the necessity of direct palette printing, and I will tell you the conditions where the direct palette printing could be useful to you, and what kind of challenges we face when we print material in the palette form. And some of the case studies are there that will be discussed with you all. So here you can see the presentation outlines. So here first I will tell you the challenges with fused filament fabrication in relation with the direct palette printing, and then I will discuss the necessity of palette based additive manufacturing or palette based 3D printing system, then advantages offered by palette based additive manufacturing system, then we have some case studies and future scope. Okay, so let's start with the fused filament fabrication. So this particular means process has been covered by various speakers. So I will not take too much time on this. Here I will just summarize. So in this particular process, we feed material in the filament form. So the material is fed by using two rollers. So you can see a schematic diagram is here. So let me explain the feeding principle of material of this particular of this triple F process. So this black one is the filament, right? And these green one are the rollers. So they actually rotate and they help in the feeding of this filament form of material into this liquefier head. So this brown one is the extruder head or the liquefier head. So you can call it you can name it like liquefier head or extruder head, right? So these rollers basically are used to push the material in this opening. So here we have a small opening in which these rollers push material, okay, or these rollers feed material into this particular opening which we have in the extruder head. So how the material is extruded means in AAA process. Can anyone explain? Because this process has been covered by the I think many speakers in this particular FDP. So can you tell me what is the extrusion mechanism of AAA? How the material is extruded at the end of the nozzle, or how the extrusion of material uh, is happening there? Hmm? Anyone? Means how we are getting material at the end of the nozzle. Here if you see, the material is being extruded from the nozzle. So how it is happening? Because there is no plunger mechanism, there is no screw mechanism. What we have studied, for extrusion purpose we need to use some sort of mechanism. We can go with the screw and barrel mechanism, and we can go with the piston and cylinder mechanism. So what do you think, how the extrusion of material is taken place here in AAA? Can anyone of you explain the extrusion mechanism? Anyone?
Through the rollers.
Hmm?
Through the rollers, sir.
Through the rollers. Oh, no,
Yes.
roller actually are playing indirect role. How can you do the extrusion by using roller directly? Roller is just a component, okay, that is basically we are using to feed the material. But how the extrusion is basically is taken place here? Roller, okay, roller is basically, you can say, it's the power source, or because they are these rollers are rotating, so they are basically helping us to feed this material in the small opening. But where is screw and the plunger? Have you ever thought about this, or how we feed the material in the, or sorry, how we extrude material in the AAA?
Sir, filament itself act as a plunger, sir, in this.
Yes, this is the correct answer that I wanted to know from your side. Because filament is entering in the solid form, right? Because here the filament in the solid form, and when the filament is entering into this liquefier head, it acts as a plunger itself. Okay, so filament itself acts as a plunger, or we can say piston. So that's why the extrusion of material is basically is taken place at the end of the nozzle opening. Okay, so this particular aspect of the AAA process I wanted to cover with this slide. So now let's move to the next slide, and let's see what are the challenges. I am talking about the material feeding aspect here because different challenges have already been covered in the previous lectures. So here I am going to discuss about the challenges with respect to the material only. So first challenge is it requires the formation of filament. It means we have to convert the material form into filament. So whatever form we are having, if we convert that form into filament one, then only one can feed the material in this process. So formation of filament, this is the first challenge. Why I'm calling it challenge? Because filament itself means should have the uniform diameter. Because yesterday I have discussed so many aspects related to the filament preparation. So challenges, porosity, lot of things are there related to filament. So that is again very challenging task, right? Then second is the requirement for materials with specific mechanical properties. Because with this discussion which we have done on this AAA, so one thing is very clear: filament should act as a piston. Filament should act as a piston or plunger. Then only you can get material through the nozzle, or you can extrude material through the nozzle. Otherwise, you will not be able to extrude material from the nozzle. Okay. So what are those properties? What are those mechanical properties that I will tell you? This is one of the property that should be there. So what happens when we what that is the column strength. I hope everyone has already studied about the column strength in the strength of material syllabus. So I assume you know about the column strength. So what happens when the elastomeric materials or the flexible materials are fed means into the triple A process? If you are having means highly flexible material with you, and suppose you want to print it through the, or you want to make some parts by using that flexible material through triple F, then what will happen? Because flexibility is highly flexibility is there, so what will happen? The low column strength will be there. So along the z direction it will have the low column strength. If you push, if you take a cylinder bar of that material and if you try to push it, or if you try to apply the compressive load on it, it will bend. So what will happen when we try to elastomeric material through the rollers of triple F? So you can see I have taken two cases. So this is the first case, that is that is showing the feeding of rigid material filament. Rigid material means like ABS, PLA, and other nylon and other type of plastic materials. So when we feed the rigid material through these rollers, so roller position you can see, there is no problem. When we feed the rigid filament material from these rollers, then we will not face any kind of problem. And this filament will act as a plunger when it will be entered in the extruder head. But once we feed the flexible filament through these rollers, then what will happen? You can see the consequences of the flexible material filament feeding. So what will happen means, because these rollers are rotating, right? Suppose these are rotating like this. Okay. And due to the rotation, the rollers will push the filament into the downward direction. And here, since we are having very small opening, here we are having very small opening. So what will happen when we push the elastomeric material through these rollers into this opening? Then buckling may occur, or bending or buckling issue will be there. That will be very prone. Okay. So part printing of highly flexible materials is difficult when we try to do this particular task through triple F, because the material itself unable to produce appropriate force. Because from the discussion we came to know the filament should act as a plunger. So the flexible filament will not be able to produce appropriate force that is required to push viscous melt against the nozzle opening. Because nozzle opening here, let me go back. So here you can see this opening is quite large as compared to the nozzle opening. So nozzle opening is very, very small, that is around 0.4 mm. And here we have opening around 1.8 mm, let's say. So if you compare 0.4 with 1.8, then this is quite larger, or quite means much higher than this. So if we try to push the viscous melt, because here we are having viscous melt, right? Here. So when we try to push viscous melt against the small nozzle opening, that is 0.4, then lot of compression force is required, or a lot of pushing force, or high amount of pushing force is required. So the flexible filament which we are trying to feed through in the triple F, that will not be able to generate that much pushing force. Is it okay? Is it clear? So that's why we will have buckling here.
That's why filament will buckle when it is fed into the liquefier or the extruder head. So this is these are some of the challenges which we face during the flexible material printing with triple F. Right now, so what may be the solution of this? What may be the solution? So one can is propose that solution that can be based on the direct pellet printing. So what is the direct pellet printing? So here means in the direct pellet printing systems, we can directly process material in the pellet form. So instead of making the filament, we can process pellet form of material directly through these systems. So what are the advantages? So you can see here I have taken the some pictures from the internet. So you can see here this is quite similar to the filament based 3D printing system, but here we are utilizing the pellet form of material. Instead of filament, we are utilizing the pellet form of the material. Okay, and controlling and each and everything is same as we have we do with the filament based 3D printing systems. So here you can see upper part is there, middle part is there, lower part is there. So lower part extruder is quite same, but here we use means barrel and a screw mechanism, right? Or we can use the separate plunger and barrel plunger and cylinder mechanism. Okay, and upper part is basically contains the mounting bracket and stepper motor. So motor can be mounted on the top, and then we can connect it with the help of we can connect it with the screw. The screw will rotate and it will help in the feeding of material, and also it will help in the extrusion of the material from the rotor. So let's move to the advantages. What are the advantages with direct pellet printing? So first advantage is the reduced melt solidification steps. Reduced melt solidification steps. Second is the elimination of filament extruder system. Third is the support direct recycling of waste. So reduced melt solidification system means now we are not going to prepare material in the now we are not going to prepare filament of the material, so we can directly process it. Whatever form is there, we can process it. Other than filament, if we have means material in the powder form, or we have material in the pellet form, then we can easily process it directly with the direct pellet printing system. Then elimination of filament export system. So obviously, because we don't have the material in the filament form, so we can eliminate the filament export system, and one can come up with the new type of extruder system. Then next is the support direct recycling of waste. Support direct recycling of waste. Suppose you are having some sort of waste material or waste polymer material, or you want to reuse that particular waste material, then you can use shredder and you can convert that waste polymer into the small pieces. Then you can feed that material into the direct pellet printing system for the part fabrication. So in this way, the waste recycling is also possible. Then reduction in the cost of material, because filament preparation itself is very challenging task. Yesterday I told you about the filament preparation steps. So if you compare the pellet and filament form, for example, these are the pellets and here we are having the filament. So the filament, because injection molding is one of the popular process that uses the material in the pellet form. So pellets, if you search about the pellet material, then almost all the pellets are available for 100 to 200 rupees per kg. But when we go to purchase the material in the filament form, it starts from 500 to it starts from 500 rupees up to 3000 rupees or 4000 rupees per kg. So depending on the quality, you can or one can purchase the filament form of the material. So reduction, because obviously when the material is available at low cost, one can easily reduce the product cost also, right? The increase in the number of types of polymer that can be recycled. That can be recycled. Because here we do not need to convert the material in the filament form. So obviously more number of materials can be added, or also the more materials can be recycled easily, because we need a shredder that can be used to convert those waste material or those polymers into these small pieces, and those small pieces of the polymer can be used directly with the direct pellet printing system. Okay, so the reduce embodied energy from eliminating a melt cycle, because one cycle we have eliminated, so obviously it will reduce the embodied energy. So energy saving is there. Then eliminating the time required to manufacture filament, because a lot of time is involved in the manufacturing of filament. So that time can be saved easily, and also in this way we can reduce the lead time of manufacturing of any product. Okay, so with these advantages, means the direct pellet printing system is obviously is more beneficial over the filament based printing systems. So we will discuss the different aspect of this particular process. Okay, this kind of mechanism we should use. So these aspects will be discussed in detail. Another and foremost important the advantage with this particular process or with this kind of system is the here what I told you, it reduces the embodied energy from eliminating melt cycle, right? And also it reduces the melt solidification step. So this can be means understood easily by with the help of this slide. So here I have compared the manufacturing of filament, and here I have compared it with the manufacture of pellets. So you can see if we try to prepare, because yesterday we have seen the polymer composite processing for additive manufacturing. So if we suppose try to prepare polymer composite through the through the AAA process, then what will happen? And if we do the same thing with the direct pellet printing system, then what will happen? So here you can see yesterday we discussed about this particular diagram. So we start with compounding, then we go for the extrusion process to prepare the filament, and then we go for 3D printing, then we go for analysis. But what happens when we remove the filament from the process? So here you can see one cycle is removed, or one step is removed from the uh, manufacturing. Okay, so you can see compounding is followed by 3D printing directly, because compounding and extrusion both can be done simultaneously at this stage. Okay, compounding as well as 3D printing, these can be combined easily when we process material in the pellet form. Then we can go for analysis. So cycle has been reduced now, and also it has simplified the polymer composite preparation. Okay. These can be combined. Okay, these can be combined easily. So what are the different methods we have that could be used for the direct pellet processing? So here we have two methods. One is the plunger based extrusion system. Second is the screw based extrusion. So the first diagram is basically showing the working principle of plunger based extrusion mechanism, and second one is showing the screw based extrusion mechanism for polymer processing, polymer pellet processing. So what do you think, I mean, which one is more beneficial? Can you, can you share your thoughts on this, or according to you, which one is most advantageous?
Screw based.
Screw based. Why? Why?
Feeding is better.
Feeding is better in what terms? Feeding is better. In what way? Means you are saying feeding is better. Then what factors you are considering, or what things you are considering to say feeding is better? Yes? Anyone? Anyone, please? Make it interactive, otherwise you will not enjoy this lecture. You can make it interactive. We can discuss some of the aspects related to a direct pellet printing system. Then only we can enjoy, or we can miss.
Sir, I think it will have a proper mixing.
Okay. It means which one?
Screw based one.
Okay, screw based one. You are saying screw based is provide the better mixing.
Yes, compared to the plunger.
Okay, plunger. Any other benefit? Means only single benefit is there, or on any other benefit is there? Any other benefit other than
so in screw based extrusion, continuous material can be we can fill up. Means
good. Okay, second benefit. Okay, good.
Better material flow. Better material flow.
Better material flow. Actually, I'm not getting your voice. So pardon. No. Okay, so two benefits I have come across. First is the better mixing, and second is the continuous feeding of the material. Okay. Now let's see. Now, actually, in the next slide, I have done the comparison, or I have made comparison of these two possible method of direct pellets. So let's see what are the. Okay. So now let's see. Let's move to the comparison. So plunger based systems are simple to operate, because simply we need to apply some pushing force, or we need to actuate the piston in single direction. Okay, so they are quite simple to operate, but as one advantage or one answer I got from your side, so that is the discontinuous extrusion of materials makes it ineffective for fabricating the larger object. Suppose your objective is to make large part or large size part. In that case, you have to process large amount of material. But because we have limited volume of cylinder, so we cannot go beyond the available volume. So that's why these kind of means system or plunger or piston based systems are not suitable for fabricating the larger objects. While if you look at the screw driven 3D printing system or screw driven systems, they could feed the material continuously because we are having rotating screw, right? So we can feed material directly into the hopper, and from the hopper material will be fed into the uh, space that is there in between the screw and barrel. Okay, and one more advantage with the screw based mechanism is it allows a more precise control. So better mixing means what we were discussing in the previous slide. So it allows a more precise control over the extrusion process, associated with improved capacity to generate pressure, homogenize the molten material, and allow some level of mixing. So that is the most important advantage which we get from the screw based extruder systems. So that's why when you are planning to make a direct pellet printing system, you should go with the screw based extruder systems until unless material is not that much in the liquid form. Suppose if your material is highly, or your material is less viscous, then you will face some problems with screw based extruder system. Otherwise piston based system can be useful. In that cases piston based system can be useful. Okay, so I have some case studies that I have performed during throughout my career, so I will discuss with you. Okay, so I have already carried out some work on the direct pellet printing, so that I will discuss here. So first case study is the in-house development of direct pellet printing enabled additive manufacturing system. So because for any kind of research we need to develop a direct pellet printing system. So how we have done it means, or what way we have developed a direct pellet printing enabled additive manufacturing system, so that I will discuss. So you can see the schematic diagram of the developed pellet based additive manufacturing system. So you can see in our work we utilize the CNC machine, CNC milling machine, or we can call it a CNC machine center. So what we did actually to convert this machine into the additive manufacturing system, we designed and developed a material deposition tool that was having the compatibility with CNC machining center. So we were able to mount the material deposition tool uh, by using the standard spindle or standard tool holder in the spindle of the machine. Okay, so you can see the mounting of this particular tool on the CNC. So this particular diagram is the schematic diagram, right, which we have prepared in the software. But actually actual view of this particular setup you can see in this slide. Okay, so this was the whole setup which we developed to convert this machine into the direct pellet printing system. So you can see here we are having supporting frame, and on the top we are having one hopper, and then we have here a barrel, and inside this barrel we are having one screw. Okay, and here we have some wires. So these wires basically are related to the thermocouple and heater. Okay, so band heater actually we used in this work, and at the bottom we have small nozzle. So this is the setup which we develop to convert this particular machining center into additive manufacturing system. Now you can see the different components, the details I have given here. So hopper is there, CNC tool. This we have taken directly from the machine toolbox. Okay, then a screw is there, barrel. So these things actually we develop in-house in the institute itself, and this one was taken directly from the machine accessories. So initially we thought to print ABS material. Why? Because we were printing the ABS material for a long time with the triple F system. Okay, so we knew the parameter related to ABS. So we started experimentation with this ABS material. So because this material was the standard material that was available at that time for 3D printing systems. So we try to make some parts by using ABS material. So we faced a lot of issues initially because our system was not optimized, and also the design was not optimized. So blockage at the entrance of the barrel and varying extrusion diameter we obtained in the extruded materials, and also the material degradation due to excess heating, discontinuous extrusion of the material sometimes we observed, then warpage within the parts, right? After that means we did a lot of modifications, and uh, then we again we again went for the experimentation, and we try to print other materials. So the results I will show in the next slides. So in order to convert the machining center into additive manufacturing, we develop our own customized software module. So you can see here we merge all the necessary steps that are required for additive manufacturing, like STL, import, slicing, toolpath, GM code. Yesterday, Professor Jan has already explained the STL related parameters or STL related problems can be solved in the MATLAB software. So this particular graphical user interface or software was developed with the help of MATLAB. So you can see here we have all the options like STL import, slicing, toolpath, GM codes. So GM code we generated the compatible GM codes, means the codes which were compatible to the CNC machining center. Okay, and other parameters like layer thickness, feed rate, screw speed, because we were using the screw speed in our case, in our case. That's why screw speed was very important parameter. So we have provided one provision here to change speed in the given range. Okay, so that speed we can change by just adding us that value here. Raster angle and root gap, number of cells required for and during the printing. So these parameters could be changed by using this graphical user interface directly, right? So here are some of the features of the developed customized software module. So import and processing STL. So import once the STL was imported in the MATLAB, so you can see it was looking like this. All the triangles are visible, okay, and also color coding was provided to make it more interactive, right? And slicing was done in the customized developed software. So all the slices or all the layers can be seen clearly, and also the toolpath generation. So toolpath, so you can see here, we have developed a toolpath, or we have generated a toolpath that is known as crisscross pattern based toolpath. So one layer is deposited at this angle, and another layer is deposited at 90-degree angle, or just perpendicular to the previous one. So that's why this crisscross pattern is obtained here. That's why you can see the crosses, right? And if you look at this code, the code that we have opened in the notepad. So you can see here we are having G00, G00, G01, M04. So M04 we use for the anti-clockwise rotation of the tool. In the standard machining operations, we generally use M04 to rotate the machine tool or the cutting tool in anti-clockwise direction. So here we were using the screw. So that's why we have rotated our screw in the anti-clockwise direction for the extrusion purpose. Okay. So depending on the screw profile, you can select whether you want to rotate your screw in clockwise direction or anti-clockwise direction. So that decision can be taken based on the screw profile. Another factor you can see M05 for spindle stop. So once we feed this particular code into the machine, at the time spindle will be stopped. Okay. So you can see we have added all the standard codes that are acceptable to the CNC machine. Okay. And here are some other shapes you can see. This is for the circular profiles. This is for the star shape profiles. This is for tensile specimen, dog bone specimen, and this is one of the part geometry in which we are having a through hole at the center. So our customized software module was able to generate the tool path for this kind of geometry also, right? So these are some of the parts which we have printed by using the ABS material. Okay, so ABS material you can see initially this kind of quality actually we achieved. Later on we improved the quality, so that those details I will show later on. So this actually first case study was the development of direct pellet printing system with the help of CNC Machining Center and printing with ABS material or the standard material, right? In the next case study, we extended our work toward the flexible part fabrication because we knew the challenges with FFF when we go for highly flexible materials through FFF, then we know the challenges. Okay, so due to those challenges, we extended our study toward the flexible part fabrication using EVA material. So if you search about EVA, then this material is highly flexible in nature, and this material is not available in the current library of FDM or FFF. So that's why we were very curious to know the part property of EVA printed parts. Okay, and our system was capable to accommodate rigid as well as flexible materials because we were using we were feeding the material in the pellet form, right? So you can see the material which we have taken. So these are the pellets of EVA material. Okay, so they are quite transparent in nature and they are very flexible also, right? So initially, in order to check its extruded extrusion capabilities, we try to extrude this particular pellets through our system. So this kind of means filament we obtain during the first trial, right? Then later on, once we confirm the feasibility of EVA material through our system, then we have extended our work toward the part fabrication. So you can see the quality of printed parts which we have done with EVA material, right? So this kind of parts we printed, and also the flexibility you can see here. We have one specimen, that is the dog bone specimen that we use for tensile testing. So here manually this specimen is twisted. So twisting results you can see here. So it was having the ability of ability to twist. So we were able to twist it in this manner. So it shows the flexibility within the printable specimen, or sorry, printed specimen. So in order to confirm the flexibility, we conducted one test that is known as hysteresis test. So the result of that particular test can be seen here. Okay, so what we did, we captured residual deformation percentage with respect to the given deformation percentage. So we deform a specimen up to a certain limit, then we release forces from the specimen, then we check how much residual deformation is there, or how much deformation is left after releasing the force. Okay, so you can see up to 60% deformation, only 1% residual deformation was there, or it we can consider it as zero. Okay, 1% is nothing, that is very close to zero. So we can say the filament, sorry, the parts which we have printed using this EVA material were highly flexible in nature, and they were having capability uh, to capability of dissipating energy. Okay, so that's why residual deformation is almost 0 up to 60% deformation, right? And here in this picture you can see the bonding between the deposited rods of EVA. Okay, so this is the outer cell, and this one is the infill infill material. So bonding, you can see, this is the microscopic view of the deposited rods. So bonding, you can see that is quite good, and material were having the good flexibility and also good bonding. Then after fabricating the flexible parts using EVA material, we conducted one more study in this direction, because today Professor Singh has discussed the smart materials for 4D printing, right? So he discussed about the conductivity within the polymer parts, right? So we thought we should go for flexible electrically conductive composite fabrication. Why? Because in literature we found that very few researchers have conducted studies toward the conductive polymer composites, right, using triple F. And you can see here we are having thermoplastic urethane, that is HIPS, and the material filler material they used, that is CNT or CNF, graphite flake microparticles, and electrical conductivity was evaluated by them. And in the next study you can see ABS material, graphene material is there. Electrical conductivity was one of the property which was analyzed by the researchers. So almost in this particular table, if you see, then all the materials, all the polymer matrix are rigid in nature, right? So that's why we thought we should explore the flexible aspect along with the electrical conductivity, right? So we search the different application or the need of flexible electrically conductive composites. So you can see the various applications of this particular composite material. So it is used in health monitoring, displays, pressure sensors, flexible circuit fabrication. And so we thought, because these applications are there, so we thought we should explore this EVA matrix as a flexible matrix or flexible matrix in the flexible electrically conductive composite materials. So we extended our study toward this direction because due to these applications, right? So in order to prepare the electrically conductive flexible composite, we considered EVA as the polymer matrix and graphite as the filler material or the reinforcement particle. Just wait, I think some technical issue is there.
I hope there is some connectivity issues, so I will check. Just a minute.
Yes, sir. Yes, sir. Now it is solved.
Okay, okay. Yes, sir. Please carry on.
Okay. To develop the electrically conductive composite, we consider EVA as polymer matrix and graphite as the conductive material. So you can see different proportion were considered in this study. So 80%, 88% EVA and 20% weight percent graphite was considered as one of the sample, and 70-30 another, 60-40 third one, and fourth one. So four means different proportion of these two material means were considered in this particular study. And then you can see the methodology we adopted to develop the compounded material and the composite parts. So here I mean we used the polymer solution method, so which we discussed yesterday. So you can see here I mean initially we prepared the polymer solution by just adding the EVA and its solvent material. EVA and solvent material, and in this particular solution we added the graphite powder particles later on, and we stir this particular solution for 5 to 6 hours, and then the composite material or the compounded material of the graphite and EVA was prepared. So after this preparation, we pour this particular material on this flat sheet, right? And we left this particular material for some hours or for few hours, and after dry it, we pelletize or we converted this particular flat sheet into the pellets. So these graphite filled EVA pellets was fed into the hopper of the developed material deposition tool. Okay, so composite pellets you can see here, and initially we extruded this material in the filament form, then again we cut down these filaments into the pellet, again we fed this material into this particular material deposition tool for part fabrication. So you can see here we obtain the fabricated parts. Okay, fabricated parts. So after means before fabricating parts using EVA and graphite compounded material, we went for characterization. So SEM, XRD, FTIR, which we have discussed yesterday. So these techniques were employed in this study. So structural and morphological changes were analyzed. So you can see here this particular SEM images actually showed the presence of graphite particle in the EVA polymer matrix, and in this particular slide you can see EVA spectrum for which we obtained from the FTIR and XRD. So you can see the both peaks are available. One is for EVA and second is for graphite material. It shows the presence of graphite in the EVA matrix. Okay, so randomly we have we chosen the samples, and accordingly these tests were conducted, right? And after conducting the structural and morphological analysis, we went for the rheological behavior. So rheological behavior, as I told you, two properties are very important. One is the melt flow rate, that can be measured by just checking the melt flow index, MFI. Okay, so in order to check the melt flow rate of the developed composite material, we use melt flow index tester. So you can see here the schematic representation of the melt flow index tester. So this is the standard method that we use to check MFI of any material. So here in this method we heat the material at up to 190 degrees centigrade, and then we applied different weights according to the standard on it. So generally material extruded for 10 seconds, but the unit of this particular MFI is the gram per 10 minute. So later on we can convert it into the gram per 10 minute. Okay, So the gram per 10 minute MFI is listed here. So that can be seen through these graphs. So the black one is showing the MFI values for the developed composite for different weight proportions, and this blue one is showing the extruded diameter, because yesterday I told you swelling is one of the most important parameter, right? Because from the diameter which we obtain from the nozzle opening, that is more important to select the value of layer thickness, road width, and other parameter related to additive manufacturing of 3D printing. So that's why these two parameters were listed or quantified by using these kind of analysis. So here in this particular slide, you can see the printed specimens or printed parts which we have made using the EVA and EVA graphite composite. Okay, so this cave specimen was fabricated for the electrical conductivity testing. However, for tensile testing, you can see we have we fabricated these dog one specimens, and for the compression, you can see we fabricated this cuboid shape specimen, right? So, and also you can see one flexibility you can notice in this picture. So then the first picture you can see, this is the original printed specimen of EVA and graphite, and the second picture you can see manually it is bent into one direction. So bending is there, bending can be observed easily, and here in another direction we have bended it, right? So bending is occurred in this way. So it shows that the printed specimens were having the sufficient flexibility along with the electrical conductivity, but still we have not done any electrical conductive test on these specimen. So but in the next slide I will show you the electrical testing results on how we or how much electrical conductivity we have increased by just adding the graphite particle into the EVA matrix. That I will explain in the next slide, or I will show you in the next slide. So electrical characterization was conducted or was done by using 4-probe method. Okay, so to quantify the electrical conductivity, we use the classical percolation theory. So what is this theory? Classical percolation theory, what is it? According to this theory, the polymer composite, any polymer composite, I'm not talking about this particular work, any polymer composite can achieve electrical conductivity when the volume or weight fraction of filler material is above the specified value. So what does it mean? If we are adding, suppose if we are keep on adding the filler material in the polymer matrix, the electrical conductivity will not be increased until unless if the amount of that filler material is not above the specified value. So what is that specified value? This particular specified value, above of it we achieve electrical conductivity within the specimen, that is known as percolation threshold. So here you can see I have written the definition of percolation threshold. So that particular value of volume or weight fraction of filler material at which we are achieving electrical conductivity, that is known as percolation threshold. So schematically you can understand, or you can understand this mechanism or this phenomena. Here we have 3 diagrams, right? So you can see this gray one. Here we have 2 different material, black one and gray one. So gray basically is representing the EVA matrix or EVA polymer chains, and this black is representing the graphite particle which we have added earlier. So you can see when the graphite concentration is quite low means when there is no electrical conductivity achieved. In that case, what has happened here, you can see one graphite particle is here and second graphite particle is here. It means there is no connection between these two. And in the second situation, when we keep on increasing the graphite concentration, In this case, here 1, 2, 3, 4, 5. So 5 means graphite particles are there, but now their distance has been reduced, or that distance between the graphite particles is now decreased, or we can say now they are means coming closer. Okay. And in the third case, where we are achieving this electrical percolation, where you can see all the graphite particles now connected together, and they have formed one conductive network within the EVA matrix or within the polymer matrix. Okay. So in this way you can achieve electrical percolation, or also you can achieve thermal percolation, because most of you or might have working on the polymer composites for thermal conductivity or electrical conductivity. So in the same manner you can achieve thermal percolation also. Okay. When the filler material or the reinforcement particles form a new network within the polymer chain, then only we can achieve electrical conductivity. So this is the phenomena behind the achievement of electrical conductivity in the polymer chains. Okay. So you can see in this particular graph, little increase in the electrical conductivity, 20 and 30 graphite weight %, right? 20 and 30 graphite weight %. So initially up to 20 and 30 weight %, the electrical conductivity was not increased that much, but when we increase the weight % of graphite from 30 to 50, in that case you can see sudden rise was observed in the electrical conductivity. Okay. So 30 and 50 weight %, right? So you can see now the sudden rise is observed in this graph. So how much means improvement we obtain with this graphite addition? So you can see here 539 times increment in electric conductivity was achieved for EVA graphite 50. EVA graphite 50 means EVA and graphite both are 50-50. Okay, the proportion is 50-50% achieved than that of neat EVA. So if I compare the electrical conductivity of EVA and EVA graphite, so that was 539 times as compared to the neat EVA material or neat EVA matrix. So this was the achievement of electrical conductivity within the specimens. Then next is the mechanical characterization. Mechanical characterization. So here, because along with the electrical characterization, we wanted to check or we wanted to quantify the flexibility, or we wanted to see the mechanical properties of the printed specimens, right? So you can see significant drop in the tensile strength and elongation at break was observed after addition of graphite in the EVA matrix. So why it is so? We were interested in the reasons why it is happening. Means what is happened after the addition of graphite in the EVA matrix. So we wanted to check it. So you can see we have taken some SEM graphs, SEM images of the tested samples. Okay, so failure mechanism actually was assessed by using the SEM images. So you can see here we found some of the holes, okay, between the divided rods. Okay, some holes are here, and you can see why it is so. Why these holes are present? Because due to poor bonding. If you remember, then here I told you melt flow index rating was decreased with respect to the addition of graphite particle. So due to this melt flow rate decrease, the poor bonding was observed because viscosity was affected or flowability of the material was affected. That's why the rods were not joined together. properly. And also small holes was also observed. So you can see here the graphite particles which we have added earlier in the EVM matrix, they form defects or they created voids in the developed composite. So due to these reasons, the significant drop in the tensile strength and elongation at break was observed. Another study which we conducted on the melt flow behavior of aluminum filled ABS polymer composite. So in this particular study, we assessed the melt flow behavior of aluminum and ABS polymer composite. So we filled ABS polymer matrix by aluminum. But why we consider melt flow behavior? What is the reason behind its consideration? So you can see melt flow behavior of the material is very important parameter in the FDM or in the extrusion based additive manufacturing system, whether it is a direct pellet printing system or whether it is filament based printing system. So you can see the importance of road width and road gap, how these two values affect the bonding strength or the bonding between the roads, right? So we found these two factors are very much affected by the melt flow behavior of the material. So that's why we develop, we analyze the melt flow behavior of the developed composite material. So developed composite like AI aluminum, AL and ABS polymer matrix, these were mixed together to prepare the polymer composite. So you can see here we have taken the XRD spectrum for these two materials. So two peaks are there, one is for ABS and second for aluminum, right? And the composite was directly prepared by the melt mixing technique. So again we because melt flow behavior or melt MFI is tested by using the MFI index tester. So you can see this is again the schematic diagram of the same tester or apparatus. So these tests were conducted at 230 degrees centigrade, because for ABS the standard value is 230 degrees centigrade, that is used for 3D printing, right? So again with the same way as we have done for EBN and EB and graphite, we tested the sample for melt flow index testing. Then we measured the weight of each sample through this digital weighing machine. So you can see the weight indicator is here. So that was recorded in this table. So log of experiment, you can see 16 experiments were conducted. Parameters, extrusion temperature, extrusion load, filler loading, and these parameters were considered in this particular study. And these are the results. So extrusion load, when and here you can see the mean of means for the melt flow behavior. So when we increase the load, extrusion load, the melt flow behavior or melt flow index was increased. Okay, similarly for extrusion temperature, it was increased. Okay, but for the filler content, it was decreased. Part fabrication was done after this particular study, but I'm not going in much detail because I want to discuss this particular topic. This is very, very important nowadays, because most of the researchers are interested in the hybrid kind of manufacturing. So we extended our study toward the hybrid direct pellet printing and machining system, because our system was capable to do additive manufacturing, and we use CNC machining center in our work. And originally the function of CNC machining center is to remove material or to machine the part surface, right? So that's why we thought we should go for a hybrid direct pellet printing and machining system. So you can see here we printed some of the samples and then we applied, because we know the stair-stepping effect of additive manufacturing, right? Stair-stepping effect are there in the additive manufactured part due to the layer addition. So that can be removed easily if we develop a system that is suppose capable to print and capable to print and machine the same part, then we can achieve the part with good surface finish and dimensional accuracy. So here in this study, you can see here we are having a cutting tool. So that was basically used to remove the material from the rough surface. Okay, so originally the part was having the rough surface. So how we did it means how we develop this particular system, because our previous customized software module was able to generate toolpath for additive manufacturing. Because we wanted to perform these two manufacturing activities on the same setup, so we again generated the hybrid additive subtractive toolpath using the MATLAB software. So you can see in the same GUI window, we have provision to perform additive manufacturing and also to perform subtractive manufacturing. And different process parameters are there. So these parameters I have already discussed with you. So I'm not going in that much detail. So results you can see is for this particular part. So here this is the actual part that was printed through the system, and here we applied the machining on it. So after because for simple parts we tested our setup. So you can see the surface roughness that was before machining, that was around 19.495 micron, and after machining it was around 2.068 micron. Okay, and this CAD/CAM lab, here you can see this was machined after fabrication or after printing. So the surface is quite smooth, right? And here this is the surface tester, roughness tester, that can be used for the surface roughness measurement. Then we extended our study for the large part fabrication. Large part fabrication, because in comparison to the build platform of CNC machining center, our setup platform was quite small. Okay, so we wanted to extend this study toward the large part fabrication. Large part means the part size should be larger as compared to the small one or small parts. So we thought we should add the big platform or large build platform on the CNC machining center, and we should go for the large part size fabrication. So in this study, we added a large build platform here. You can see, right? A temperature control was there to control the temperature of the build platform, and large size platform was added into that. And here you can see we prepared some large size parts which we were not able to do so with the previous setup. Okay, you can see here easily we were able to make these kind of parts easily with the existing setup. Okay, so this part size you can see, you can see it is having the large size, and outer shell was deposited with 100% infill density, and inside surface area was filled with less infill density, right? So this program was again generated by using the MATLAB, okay, with variable infill density. Then another study which we conducted with this setup That is the exploration of Hilbert toolpath pattern. Hilbert toolpath pattern using direct palette printing. So here you can see why we have explored this Hilbert toolpath. Nowadays it is available in the existing or the commercial softwares. So you can choose directly from the software itself. But when we conducted this particular study around 2015, at the time this particular toolpath was not available in most of the softwares. So we thought we should explore this particular toolpath pattern in additive manufacturing. So why we have chosen this fractal or Hilbert based toolpath? You can see here I have taken the raster based toolpath pattern in this. Okay. So you can see that the temperature gradient, if you compare, means the temperature of this particular point and this point, then the temperature difference is quite high, or temperature gradient is much more as compared to this one. If you compare these 2 points and these 2 points, because nozzle is moving in this direction and then it is going back in this direction. So since nozzle here, it will take very less time when it will move from this position to this position. That's why you can see the temperature is almost same here. But if you compare these 2 points, so nozzle has traveled long distance here and again here. So due to this distance travel done by the nozzle, the temperature difference will be larger. So due to this temperature difference, the bonding between these 2 points will not that much good. So this particular delay due to the distance traveled by the nozzle is known as delay time, right? So this can be removed if we go for other alternative tool paths. So we wanted to see the effect of Hilbert curve, how it is affecting the delay time feature, right? So because since it is having very short rasters, so in this particular toolpath, nozzle comes back in very quick time, hence less delay time is there. So you can see the toolpath pattern that is very that is having very small rasters in that. Okay. So effect of tensile strength, effect on tensile strength we have observed. So you can see how we prepare the fractal based toolpath. So you can see this is the contour of tensile specimen, and you can see this is Hilbert curve, and this is Hilbert curve for a square, right? Then we trim the fractal curve, or we have generated this fractal curve here, you can see, and then for different orientations we printed these specimens. So you can see for Hilbert curve based toolpath, the tensile strength was increased, right? Hilbert curve based toolpath, tensile strength was increased due to the less delay time. Okay. Then another study which we conducted on direct palette printing, that is basically the low cost solution. Why I'm calling it low cost solution? Because in all the previous studies we explored the CNC machining center. CNC machining center. So if you look at the cost of CNC machining center, that is very costly. That is quite costly as compared to the current additive manufacturing system or the current filament based 3D printing systems. So what we did, we thought we should propose a low cost solution for direct palette printing, because everyone cannot afford the CNC machining center, because the cost of CNC machining centers is in crore or in lakhs, right? So what can be the low cost solution for this? So you can see what we did. We purchased a filament based system from the market. Okay, so we purchased a commercial ANET A8 3D printer directly from the market, and you can see here we replaced this filament based extruder system by pellet based extrusion system. So we developed another setup, another small setup that was compatible to this one. Okay, so this one was replaced by this one. Now you can see this is the actual CAD model. Sorry, this is the CAD model, and this is the actual setup. So this setup basically is mounted on the ANET A8 printer. So this is CAD model, and this one is the actual pellet based extruder head. Right? So what kind of parts we have is fabricated? So you can see during the trials, this part was printed using the setup. This part was printed, and this kind of geometries were printed by using the developed low-cost direct pellet printing system. Right? Although quality is not that much good, but it can be improved by just optimizing the process parameters and other factor also. And some case studies I found in literature, and one study is by the Alexander A. So they actually presented one case study on direct waste printing of polylactic acid with universal pellet extruder. So they have developed quite similar setup as we have developed. So you can see their setup is here. Okay, so they have made this type of setup. They have mounted on the same ANET printer, and these type of parts they have printed by using the PLA material, and they have added some sort of composite fibrous material into this. Another case study that is there, which I have taken from the literature, pellet extruder for composite thermoplastic 3D printing. Composite. So composite thermoplastic pellets can be printed easily by using this pellet extruder that is available in the market. So you can see this is developed by one of the company. So company name is the CEAD, CEAD. So you can search about it. So you can see their extruder head here, right? And they have manufactured different types of machines, and by using robotic arms, by using the CNC machines. They have developed the large size machines along with this extruder head. Okay, and if you talk about the part, then you can see the structure. They are capable to make large structures. They are having a capability to print these complex shape. Okay, so they are providing the special material for this. So if you are interested, then you can contact to them for more details. And other commercially available direct pellet printing systems are provided by various companies like Juggernaut 3D is there, Titan Robotics Limited is there, DYJD Designs is there, and IT 3D Group Direct 3D Cosine is there. So you can see their model name here in this column. Okay, the size you can see here, and size 915 mm, 1220 mm, 1220 mm. So these are the different sizes which are available in the market. If you are looking for the commercial direct pellet printing system, then you can visit their website. So I have uh, provided the address of their website, so you can visit. Okay, so what is the future scope of direct pellet printing? So considering the recent progress, there is a lot of scope for further development of direct pellet printing, but combined efforts are required because most of the researchers have means explored the manufacturing aspect of the parent printing system. They have considered only one or two materials, right? So more materials are needed to be considered, okay, and new compatible materials may be explored and their application may be find out, okay, which are still challenging today. And you can come up with the potential printing strategies so that we can compete with the traditional molding parts, because traditional molding parts are having much more superior quality as compared to the additive manufactured components. So we have to come with the new type of strategies, new type of post processing techniques, new type of printing strategies to counterpart the or to counter the molding parts, right? So we all know the capability of additive manufacturing systems. They are having they are having capabilities like complex part fabrication. So these would be the driving force for future scope of the development of novel compatible materials and to explore their potential applications. So with this, now I request to all of you, if you have any query, then
Thank you, sir, for this wonderful discussion. Participant, please ask your queries if you are having any. We are now open for the queries. You can ask.
so now if you have any question regarding the discussion, then you are most welcome.
Yeah, because actually
I
we
would
are
be
just
happy to
already,
answer.
our next expert has already joined us, Mr. Pradeep ji. He's an industrial expert, and he will explore about some 3D printing related softwares, which are nowadays very impactful and fruitful for developing your own models and research perspective completion. So otherwise we can begin with his talk, I think.
Participants, any query? If any query is there, then you are most welcome. You can
Yeah, rather
raise
you
your
can
hand.
write your queries in the chat box, or later on you can continue with that, no problem. Either you can directly write
So I
emails
am
also.
giving means 1 more minute to you. After that, we will start the next session
Yeah,
because Mr.
yeah.
Pradeep Kumar has already joined us. So he is the application engineer at Integrated Microsystem. So I can wait for 1 minute.
One more minute we can
One
wait,
more minute. We
then
will
we will
wait.
start.
Dear participants, please don't leave this meeting now because we have another session as per the given schedule.
Yeah, it's a kind of a additional
Yeah.
session we have added up into this planned program, so that our most of the participants can be more benefited out of his talk. So that that's the real kind of softwares which our industries are utilizing actually. So that's going to
Because we know the importance of additive manufacturing in biomedical applications. So it will be interesting session. You will learn about the medical imaging and the medical modeling. So just be there, okay? We are going to start the next session. So before handing over the platform to Mr. Pradeep, let me introduce him first. So Mr. Pradeep Kumar is the application engineer at Integrated Microsystem. He works with image processing tools, material modeling, CAD, FEA, and CFD models based on 3D image data. And he looks over the technical support for simpleware software and closely works with simpleware customers to help them with their designs, research, and modeling needs. And he provides live demonstration to various IITs, NITs, hospitals, and test faculties of various institutes who are working in the field of 3D imaging, image processing, medical devices, patient specific implants, 3D printing, digital rock physics, material modeling, manufacturing, and simulation. So with this brief introduction, now I welcome Mr. Pradeep. So Pradeep, Mr. Pradeep ji, are you there? Can you hear me?
Yes, good evening, sir. Good
Good
evening,
evening ji.
everyone.
Good evening, Pradeep ji.
Yes.
So, shall we start, sir? Or,
yeah, you can start. You can start.
Yeah.
Pradeep ji, please start.
Okay. So, I will just start by sharing my presentation first. Okay, so I hope, sir, my screen is visible to everyone.
Yes, it is. It is.
Okay. So, thank you, sir. Thank you for introducing me, and thank you for giving us this opportunity to represent our software in your FD. Okay. So, for this today's session, we will have two parts. The first part, there will be a presentation only, in which I will cover the basics of like medical image processing, and I will discuss a few case studies, and then we will move to the software part, and where we will see how to create a 3D model from medical images, or we will also see some surface deviation between manufactured part and as CAD design part. So I will begin with my presentation first. Okay. So before that, now I will discuss about this. What is 3D image processing? So we can discuss this 3D image processing as we know that this image processing is a method to perform some operation on an image in order to get enhanced image or to extract some useful information from the images. It is a type of signal processing in which input is an image and output may be image or characteristic feature or the feature associated with that image, or like that image that we get from MRI, CT or micro CT scanner, and after that we apply few tools like transformation, filtering, image segmentation, and few morphological operations. So then we get the final model. This is the like called the medical image processing. Now we'll discuss about the basic medical image processing system. So this procedure starts with the acquisition of image that we get from MRI, CT or micro CT data. Okay. It may be contact or it may be non-contact. Then we move to the processing part, and this processing part consists of these various steps. So you can see we have pre-processing of our 3D data set. Then we proceed to the segmentation. We identify our region of interest and we segment the part over where we want to focus. So we want to segment the anatomy or the part. Okay. Then is detection. We can detect any disease like tumor. We can identify any kind of soft tissue, hard tissue, the blood vessels. We can identify. We can segment these, and then we can move to the analyzing results. Okay. We will prepare the report. We will check. We will get some measurements like the cross-sectional area, volume, surface area, shortest distance, center lines, and there are so many statistics that we can get from the software. Then diagnosis, this part is done by the, like it can prepare surgical planning in a software, and that part is also be done by the biomedical engineer or and surgeon. Then you can prepare like visualizing and report. And why image-based modeling? Because we know that the adoption of this 3D imaging technology in many fields is emerging. Because this image-based modeling reveals external as well as internal feature of the anatomy or structure. Okay. Because it has application in both industrial as well as medical settings. And we also know that the demand for this realistic simulation is increasing day by day because of the expanding capabilities of finite element analysis and CFD codes. Okay, this is due to the increasing access to high specification hardware, and this image-based modeling allows us to study the true topology of structure and materials. So here we discuss the different parts of the 3D image processing workflow. You can see here we can have these various steps. Let me discuss step by step, and then we will also see in the demonstration part. Like, so the first step is 3D image import and visualization. And the second is segmentation and processing, and then measurement and analysis. Okay. So then we have CAD and image integration, model generation, and scripting and automation. So we will discuss by step. So and during this presentation, if anyone feels any question or query or doubt, so please feel free to stop us. So can at the end we can have a question and answer session. Okay, so this is the 3D image import and visualization. So we have option like we can import image of like say MRI, CT, micro CT, confocal microscopy, fibs and images, 2D stack of images, and raw images that we can also import in any software. And we also have an option to co-register of like multiple data set, the MRI with CT, then we can co-register the multiple data sets. Then we can visualize our data set by using volume rendering and the many setting tools for visualizing the data set. So, and wide range of image quality improvement tools are also available to like reduce noise, artifacts, smooth and smooth the images. So we have these options for image import and visualization of our data set. Next, you can see here, these are the various import format. If we are into the field of this medical image processing or this reverse engineering or non-destructive testing or additive manufacturing, that we know that these various formats. So DICOM, we already know, and DICOM D images is more related to industrial. It is for DICOM D for reverse engineering or for non-destructive part. Then we can import raw image data, 2D image stack, or in the format of BMP, JPEG, .png or TIFF file. These images we also get from the micro CT scanner if we want to analyze the microstructure of a rock or a material to see the the various phases of porosity of a material. Okay. We can also import, we have option, you can start work with the STL, PLY or .IGS or STP file. Okay, now next is segmentation and processing. So for segmentation, you can use various tools. Like you can approach by utilizing manual tool, or you can use a few semi-automated tools for segmenting the region of interest. Like we can utilize this thresholding tool to select a range of grayscale value that can identify your your region of interest on which you want to focus. Okay, then you can also use a region drawing tool. Later we will discuss in the demonstration part how to use these tools for segmenting, for preparing our model for 3D printing. Okay. Then we have flood fill, or you can use like this water-based segmentation, grayscale-based slice-to-slice propagation is also there. Next is measurement and analysis. So you can get the measurement as per your requirement. You can see here, this is a blood vessel showing the cross-sectional areas or the radius, diameter, length of the veins, arteries. You can see here. Okay. So you can also find out the shortest distance, or you can get the calculation for angle, volume. You can fit a sphere to check the sphericity. You can also get the measurement of holes, porosity, volume fraction. You can see here. So there are lots of tools available for this image processing workflow. You can see. Next is this CAD and image integration. So I'm just discussing this. This is the general workflow of this image processing, or you can say any kind of software if we are into this field. This is CAD and image integration. You can import, let's say, if you are into a field of like patient-specific implant design, then you have option to import any CAD design implant into the simple web software, where you can integrate your CAD design implant with the medical data set. to check the best fitting of the implant, and then you have option like you can prepare the finite element model for simulation, and then you can check the best and the worst fitting of the implant, and you can also check the stress and the load that on the implant. Okay. So here you can see this the implant and the image integration here, the stunt with this coronary artery integration you can see here. This is also the implant integration with this femur. Next is model generation. Okay, so depending on your requirement, you can prepare your model. Let's say you can prepare a surface model for export to 3D printing. Okay, so you can also provide some kind of lattice structure to your 3D model to reduce the volume or to provide the strength to our 3D printed part that we are going to print. Okay, and we can generate a volume mesh model according to our solver requirement. Whichever solver we are using, we can generate the finite element mesh according to our solver. Let's say we are using Abacus, NCS, or Edina. Then we have option to define the material property or to define the contact nodes at points or to define like the materials, or you can also define the element type. Okay. So based on the solver requirement, we can generate a model specific to solver. Next is we have this scripting. So you can, as you are already aware of this, scripting is so. 1 second. Okay. Okay, so these are the various we can say export format that are available. So if you are working on this image processing workflow, then you have option. You can export your 3D model, such as you can export it as a segmented image in raw file. Surface model you can export as STL, IGS, NC surface, Abacus surface, MATLAB file surface. Animation you can also export. You can take screenshot, 2D and 3D screenshot. 3D PDF you can also export. You can also generate a virtual X-ray with object burning. Okay. You can export in VRML or .3ms or OBJ file. For FE model export, these are the like export format that are supported by the softwares. And export in Abacus, Edina, NCS, Con4, CK. These are the various formats. CFD also you can export. Fluent, Abacus, OpenFOL, NURBS model export for non-uniform rationalized B-splines. It is .stp and IGS. So I'm discussing about the scripting. So as you know that the scripting is used to more easily perform repeatable tasks such as optimizing the segmentation and landmarking scan bonds, with the latter being used to create axes and references for the simulation. Here you can see how you can use the scripting to automate your some part of your workflow. So you can convert your load, the operation, the sequence of operation that you perform on any data set, then you simply right click and you can convert it into Python script. Okay. Python and C#, two options are available. Okay. The software has inbuilt API for macro decode. Okay, so build plugin are also supported. It is fully customized solution provider. Can work with the simple team to build your own script or to build your own kind of workflow. You Okay, so now I'll discuss two case studies. As we have simpleware, so we will discuss simpleware case studies because we are the distributor of this simpleware software. Okay. So now first case study I will discuss is this segmentation and modeling of this breast tumor for 3D printing. Okay. So just giving you the overview, as you know that the 3D printing anatomical models are beginning to have a significant impact on medicine. So basically in this case study, a model of the breast along with this tumor, see here, is being treated so that the patient could better understand the diagnosis and the subsequent treatment, the option that are proposed by the physicians. Okay, so this model were also useful for the physician, to better understand or to better visualize the anatomy of the pathology. Okay. So here you can see that this DICOM file from an MRI scan was segmented. First, it was imported into the software, okay, and then they were segmented into simpler software to generate the two 3D models. You can see here a model with the with the model of the patient with left breast, you see here, and the model of the resident tumor. You can see here. So the few tools are utilized to make this model ready for 3D printing. So use this window level threshold, crop, resampling of this data set, and mask spread fill, cavity fill, and then close, dilate, smoothing, and etc. The tools are used to segment this tumor. So here you can see that the model is generated and the 3D model of the breast, it was followed. Okay. And a post was also designed to anchor the tumor model to the breast model after printing so that we can identify the accuracy of the tumor, okay, after 3D printing so that we can analyze or we can visualize this tumor physically. Okay. Let's see. So after the segmentation, this model were exported as two STL surface model. You can see here the breast and the tumor. Okay. So after the segmentation, and these were then imported into Autodesk this Fusion 360 software for further modification for making it ready for 3D printing. Okay, and this breast, you can see here, this breast model was also divided into two halves. You can see here, to make the visualization easy. Next, it exported to this file has been sent it to 3D printer. Okay. So the breast model was printed with a transparent material, and the tumor you can see here is in the opaque material, and the post allow the tumor model to be quickly and accurately oriented to the you can see here the breast model. So, and these models are very easy to handle and present as a visual aid. So, for this, the status is GrabCAD was used for this arrangement before sending it to 3D printer. So, few colors are also applied so that you can see the tumor and the breast. So the next case study we'll discuss is this non-destructive inspection of additive manufacturing part using CT data. Okay. So for the overview of this case study, you know that the metal additive manufacturing has many advantages for producing the topologically complex design. We can say that cannot be easily achieved with traditional methods. However, the non-destructive inspection and testing of the same component is often challenging due to we can say inaccessible features, like leading to defects, and increase performance testing. So as a result, the part may be scrapped, wasting time, resources, and cost, and meaning that the additive manufacturing parts real world performance can differ from its original CAD design. Okay, so in this project, a data was used to analyze, that is a hot box heat exchanger. You can see here. This is a hot box heat exchangers. It is a good example of like complex additive manufactured part. Okay. So for the scanning of for this additive manufacturing part, okay. So the hot box used in this case study is a test jig used to determine the performance of a particular structure before customized heat exchanger is created. You can see here. Okay. So this part has a lattice structure. We can see here through which air passes, as well as the cross corrugated channels for the liquid cooler. You can see here. So making it a complex design to create using conventional manufacturing. So in addition, the physical inspection of the interior of the hot box is we can say impossible without cutting open the part. As we, without cutting it is like impossible. So next, after the scanning, we proceed to the 3D image processing. Okay, so this 3D image processing also done in the software. So the 3D image data of the part, you can see this hot box, is then imported into SimpleWorks software, like to carry out the image processing and meshing. Okay, so the few tools like the semi-automated and manual tools are used to determine the surfaces. Okay, so in this, like for image processing, few tools are used, such as filters, threshold, okay. Okay. And then you can see here in the later in the demonstration part, we will also see this. Okay, so to understand the differences between as built as designed version of the part, the simpleware, you can say the simpleware surface deviation tool was used to compare the CAD surface and additive manufactured surface, so that we can identify the deviation, first deviation of the additive manufactured part and the CAD design part. Okay. So, so basically, this method identified three areas of deviation, like for deviation, like including trap powders, and differences from the design lattice structures. You can see this design lattice structure for air passes, and having processed the image data, the SimpleWare software was then used to export a fully volumetric mesh for CFD analysis. Okay. So the generated mesh in SimpleWare software has three parts. So the first one is metal and fluid, and then air. Okay. So with assigned boundary conditions, and also you can define inlet and outlet for the fluid flow region. After generating the mesh, it was then exported, or like we can say it was then imported into console multiphysics software for simulation and comparison of thermal behavior, like including the coupled heat transfer and laminar flow. Okay. So, and the temperature distribution was the coolant flow through the channel. You can see in this figure. Okay. With the deviation in the as-built geometry, most we can say the most evident toward the base of the heat exchanger. Okay. So we can say the furthermore, overall cooling from this inlet to outlet region is greater in the as-built geometry and less uniform in the vertical axis. So as a result, the study was able to identify that the as-built part created using additive manufacturing perform worse than the original as design part. So the result of geometric differences. So for the conclusion, if we conclude this, you can see here this industrial This industrial use case is available for demonstrating demonstrating the importance of using X-ray CT, can say the micro CT. Okay. And this image-based modeling to enhance or understanding of what occurs between a CAD design and the actual manufactured part. So using this workflow, the manufacturer or the researcher can close the design loop and potentially share on cost, resting by understanding how unexpected defects and inconsistency affect the real world performance from this simulation data. Okay. Now, as I initially told you, also have option for exporting your model for 3D printing. Apart from preparing your file for this 3D printing, various options are there for making your model ready for simulation. For 3D printing, you can see here you can prepare model for 3D printing. You can provide internal lattice structure. You can have a grayscale visualization. You can apply a color map to the surface of 3D printed model representing the bone density using the grayscale values from the CT data. For the inspection, you can apply a color proofing. You can check the printability to help to get the model right first time. Okay. For the export option for 3D printing, you know that can export in the 3mm file, STL file, OBJ, and lots of files option are there for suitable for a variety of 3D printers. So now I'm just switching my screen to the software part where we can see how we can create a 3D model ready for this 3D printing, or how we can identify the surface deviation. Okay. Just switching my screen to software part. Okay, so I hope the screen is visible to everyone. And during this, if anyone have any questions, you can ask. So this is the graphical user interface of the simpleware software. You can see here. I hope the tools and text are visible properly to everyone. You can read the text. Okay, so for this today's demonstration, I will show you how to create a 3D model from MRI or CT scan, and how to segment soft tissue and hard tissue, and we will also prepare a surface model and volume mesh model for export to 3D printing, and we will also see the deviation. Okay. I'm just going to import a DICOM file and scan the folder. So here I have my file, scan it. So right now I have imported this pelvic DICOM file. Here I can see the preview by scrolling this. I can anonymize my DICOM tags. You can see here. And click here, finish. Okay, so you can see we have 4 views. Okay, out of these 4 views, these 3 views are 2D orthogonal slice view. This slice view. So we have slice in, and set this. You can see this, the current view is in medical domain related to this coronal, sagittal, and axial. I can change the view to this engineering one. And see here we have view in XY. You can see the number of slices in XY plane. In XY plane, I can see the number of slices are 280. Zero is also slice. You can see. And in ZX plane, you can see the number of slices. And in the ZY plane, you can also see the number of slices. Slice, we can say that the cross-sectional at a particular point, and the cross-sectional, I can again set this view to medical 1. Okay. And I can expand this 3D view, or on the top we can see here the few tools are arranged in a chronological manner. And here left hand side we can see the project information, spacing, image, extent, volume. Okay, and here I can see the dataset browser. Whichever I done here, the new mask will be created here. And if I'm creating a surface model, and then the new model will be here. And if I'm creating a new FE model, it will be here. And I'm creating a finite element or a physics model for elastrostatic analysis, or for finding permeability, or for calculating some elastrostatic constant. Can expand this 3D view. So this is the initial data set that I've imported into this. So it is a crop. I've already cropped this data set. It is a data set of pelvic region. Okay. I can click on this background rendering setting option. I can adjust this opacity to visualize our data set. Okay. Or we have option for preset. Say I want to segment the bone only, and select load preset. You can see here. So this is just a volume rendering. Is not a 3D model right now, because I'm not used any tool. So it is just providing me the visualization of our medical data. Can close this. Now I'm going to segment the hard tissue. You can see the bone. So if let's say if you receive a data set in a very bad quality, so you hear. So initially we have this data set in this quality. So we are not able to identify easily the hard tissue with the soft tissue and the muscles. So we have adjusted this window level so that I can visualize which part I want to segment. Selected this. Okay. It will not affect the like the geometry or pixel. It is just for the visualization of our region of interest. Close it. So I'm just beginning with the initial segmentation, and go to this image processing, and you can use few transform tools. Like you can use crop tool if you want to crop your data set. Okay, use this crop tool. You can use in 2D view as well and 3D view as well. Going to crop it because I've already cropped this data set, and I can use this resample tool. I can select or make this as a the isotropic resampling, the cubic sample. Apply this. Okay. So right now you can see it also contains a few noises. Some artifacts are also there. Can go to this segmentation. I'm going to select the manual approach, because we also have an option for automatic segmentation, and use this multi-level auth. Therefore, I just show you use 3. See here, and turn off the mask, showing this. See here, I have segmented the bone here. So, but it will not provide me that much of accuracy because here I also have to do some manual work. So, I will just try this manual approach. Can undo this. I'm going to use this threshold tool. So in the threshold, you can see here we have three options. And my main focus is to segment this bone only. Okay, close it and apply and take this because I don't want these the island type of noises. So I can take this only, keep the larger representing island because I want only this region, pelvic, head, and the sacrum and the femurs. Okay. Can click apply. And generate this fast preview. Expand it and should. Now it is a 3D model. So now we are going to segment this femur from this hip, right, hip, and this sacrum also. So we are going to split. I'm going to use this split reason. So first I will show you in the 2D view, then I will also show you in 3D how you can split the regions. So I have to identify the region where I want to split. Then add region and roughly just mark the region where I want to split the anatomies. Okay. And again add another. Because based on the mass, the Solter's distance transformation algorithm, so it will identify the distances between two parts and then split them and apply it. Close this, generate this. See here. So the splitting has been done nicely. You can see here. So now I'm going to split this sacrum from this left and right hip. Now at this time I will show you in 3D how you can split. So this is the case for this hard tissue. The same method you can apply for the soft tissue. But for the soft tissue, like the the segmentation of soft tissue will take time because they have to identify the region very accurately. So the soft tissue segmentation takes time. So that's why the time I'm just choosing this hard tissue segmentation. Again, I can add this, turn on the live 3D. Going to split this and I can add a region, again different region, click, apply, and see here. Now I can unlock this and generate a fast preview. So the model is ready, but for the 3D printing, we can see here there are lots of open cavities or boundaries which needs to be filled because we'll not 3D print that model accurately. And it's, so I'm just going to select this right femur only, and the whole work will remain same for the whole model. rename this as right filler and isolate it. Press and change the view. See these open cavities. So what I'm going to do, I'm just going to close these boundaries because initially I'm not selected that proper range of grayscale value so that it can identify the pixel which are present there. It can go to this image processing and select this paint tool. We'll just paint wherever I see any open cavity because for this demonstration, I'm just preparing this model for 3D printing. And depending on your time, you can spend time to prepare your model very accurately or to identify the pixels or the grayscales very accurately. You can prepare or you can make your model very accurately. It's roughly paint. So I'm just going to paint every after third slice. Then later I can apply a filter of 3. Okay. Yes. Okay, I can generate this. You can see this after applying the paint. Then I can go to this again, change this view to 3D, and I can apply a close filter. Here I can enter the value of 3, click apply, generate this 3D. Okay. So now you can apply cavity fill if you want. It will fill the cavity which are not touching the boundaries. Again, apply cavity fill. Now here I have option. If I want to if I want to fill this internal cavity, so I can fill it or I can make it a new mask. Let's say I'm just going to make a new mask. See here. change the opacity to 3 so that I can also see the internal cavity. Change the view to 1. So now for 3D printing, I can apply a smoothing. You can see those and enter this value 1. This. Okay, so there is one cavity here. Can fill this cavity, this open cavity. Again, I can apply a filter 1. Okay, so now it has. So at this time, you have option. So let's say I'm just going to 3D preview. I'm going to provide some kind of lattice internal structure to this model so that I can reduce the material requirement and I will provide the strength to this model. Convert this to surface. Go to the surface tool and select this internal lattice structure. Okay, just selecting the schema. I can define the cell thickness. Let's say I will keep it as 1.9. Can define the cell thickness as well, or I can make it finer. And select the unit cell type. I have selected this one, go right, and I can show you what kind of structure I'm going to provide for this internally. There are various structures. See here. This kind of structure. Just selecting this. Next. Finish. So it is generating the internal structure for this schema. Isolate the old mask. I can show you this. So this is the latest structure that I provided to this right field. I also have options if I want to fill these the lattices, the unit cell. If I want it as a volumetric, now you can go to this 3D PV and generate a model PV. Then you can click on this. Okay, go through errors. So the software also has error. Let's say if we have made any error while doing the segmentation or creating mesh. So you also have options to check and fix that error. Okay. You can see here all the error have been fixed. You close it and then can generate a model PV. And then I can export it as a STL file. Oh, okay. Cancel it. Now I'm just moving to the different project where I can show you the complete project. See here. So this is the final project. It is ready for the 3D printing. I have identified that the hip, left hip, right hip, this sacrum, with the proximal femur right and this left. So you can go to the 3D printing, 3D view, generate a nodal preview, and then you can export it. And you also have the option to write each part as a multiple file. And just show you this 3D printing. You can for 3D printing, can you have option to convert, you can work with the surface model that you generated from that image based mask. Before the preparation, a range of, here we can see the range of tool to cut or to hollow or to emboss any kind of text or to create any kind of connectors. Okay. And for this visualizations, the grayscale visualization, I can click on that, click update. I have just selected the schema. So for the grayscale visualization, we can apply a color map to the surface of the 3D printed model. We can see the representing this, the bond density using the grayscale value from a CT image data set. For the inspection, you can apply a color proofing to check the printability of your model. Let's say if you have any specific 3D printer, want to see the color proofing, you can select your specific 3D printer, and according to that, you can apply the color proofing. You can check the printability. Okay. Then you can export this to this. So for the export, you can see here, can export in TMF, STL, OBJ, PLY, the 3D PDF you can also import. Let's say if any of the colleague does not have this simple software, so you can show him 3D PDF so that he can see the complete model in 3D view, as you can see here, and also see in the 3D PDF as well. Okay. Now I'm just showing you a different project for this surface deviation. So right now you can see here, I have imported this canned gear dataset. It is already a manufactured gear. That is to okay. You can see the slices in XY and XZ and in ZY. So again, you can apply, start with the segmentation. You can use this threshold tool, blend it, and you can see the, now I will show you this profile line. You can draw a line here and see a new histogram will be quoted here. So here you just have to set the lower values and upper values where it can identify the pixels which are in between the range which I'm selecting here. Okay, pick this and create a new mask. See in this 3D view. It is a scan gear dataset. So, and after this, you can go to this 3D preview and generate a model preview. Okay. And then you can convert it into surface. You can see here, I can hide this. And I can rename this as scan gear. Okay. So now I'm going to import a CAD file. Then I will register this CAD, the scan gear with the CAD file. Go to the surface tool, select this import surface and data. You see here this CAD gear.igst file. I can open it. See, and update. So as you can see here right now, this CAD file is not watertight, has having silent intersection, is having few bad orientation, so I can fix it. Yeah, so this green color is representing that now it is watertight, it is having no self intersection, it is having no bad orientation. You can click import. See here, I've imported this CAD file. Here, this CAD gear. I can go to the surface tool and select 0 position. Expand it. See here. So now my main task is to register this CAD file with this scanned gear dataset so that I can identify the deviation between the as built part as and design part. And go to this register dataset and select this scan gear. I can update it. Next. Okay. And select here this scan gear. Here I can select this CAD gear. So here you have to provide the landmarks so that I can register it with this CAD file. Okay. And select this add landmark. I can add landmark 1 here, and 1 landmark here, and again add landmark 2. I have to add at least 3 landmarks. Here and here. 3 I can add here. And add third landmark. So I can finish. And use this snap tool. And see here, it has been registered with this data set. Okay. And turn on the visibility and delete this. So now I can go to this surface deviation tab, and here I can select my reference surface as scan gear, test surface as cat gear. Let me just show you, and I can click update. You can see here. Or you can also define this positive, critical, and negative deviation. Let's say the select it as 0.6, 2, 0.2, 6. And we go to here, set this. I can annotate the minimum and maximum. You can see here. Can now you can see the lower deviation and the upper deviation here. Or you can click at a specific point and to see the deviation, and click P here to get the point deviation at this point. So this indicates that the how much is the deviation between manufactured part and the CAD design part. Or and select this surface deviation, or I can you can compare the deviation for a specific region of part. Let's say I just select this primitive, select this cylinder, draw a cylinder here. If I want to see the deviation at a particular location. Okay, I can click update. And see the deviation at a particular point. Press P. Okay. Now I also have another data set. It is also related to this the oxidative form. As you know that the oxidative material have a negative Poisson ratio, so therefore they expand in all directions. So when they stressed, so you can see here. Initially, I have imported this high resolution 3D scan data of this oxidative form. Then I applied few tools. I segment the form and set up the boundary condition. Create a finite element mesh. See here. And see here for this model configuration for preparing a model for finite element. You can select the model type, or you can define, or you can select the export type. I've selected this as dynamic. You see here in the general tab, you can select the smart mask smoothing about pre-processing the data set. You can define the export length also. You can see the volume mesh meshing, because for this I have selected this FE grid. The algorithm I selected this FE grid because I want both hexahedral and tetrahedral element in this mesh. If you want all the element as a tetrahedral, then you can select this FE3. Material I have defined as it is a string. So I have defined these material properties: mass density, Young's modulus, and Poisson. Or you have option to keep your material as placeholder, or you can define the material property based on the grayscale data set. So that you can define the mass density, Young's modulus, and Poisson ratio according to your grayscale intensity. This will help us in case of medical. And define contact nodes, concept cell, mass refinement, boundary condition also defined. This will also help in CFD model setup. And close it and see. I'll show you how it looks like. Here you can see the element. Inside we have hexahedron, and outside we can see the boundaries are tetrahedron. Or you also have option to check the mesh quality. You can see quality inspection tool. So no error have been found for this. You see here the metrics for negative Jacobian, the self intersection in out aspect ratio as length skew, orthogonal skew. See here. You can also adjust the threshold values. So this is all that I prepared for this today's session. So I also have one data set. It is related to medical. I've already segmented this. So if I want to 3D print that head, that heart, so I've used few tools to identify the soft tissues and show you. I can generate this model to you. Because the segmentation of this heart soft tissue will take more time. You have to spend at least 3 to 4 hours for the segmentation of soft tissue. So now we are ready for the questions. If anyone have any questions, he can ask. Mhm. Then you can export. You can write each part to a separate file. Okay. So, sir, now we are ready for the questions. If any participant have any questions, so please feel free to ask.
Thank you, Pradeep ji, for such a wonderful session.
Thank you, sir.
Dear participants, if you have any query related to the discussion, which is uh, given by Mr. Pradeep ji, so you can ask, or you can write in the chat box, so he can read your questions. Pradeep ji, what is the cost of the software? I have one question. Hello.
Yes, yes, sir. So pricing, sir, can I send you an email?
No, actually, yes, I'm asking means rough idea means what how much difference there means from Mimics.
From which, sir?
No, no, actually, Mimics is also one of the software na, that is used to do modeling related to biomedical models.
Okay, okay. So which tool you are using, sir, in NIT Jalandhar?
No, no, currently I don't have any software in NIT Jalandhar, but in the past I have used Mimics at VDM Jabalpur.
Okay.
So I want to just know the difference between the.
Sir, actually, I'm from the technical background, so I don't have idea for the pricing. So if you want, I can provide you the pricing. I have to discuss with the sales team.
Okay, okay, it's okay. Whenever it will be required to me, na, I will send an email. But just I wanted to know the rough idea about the price of the simpleware software. So it's okay. I will definitely means contact in future whenever it will be needed, and then definitely I will send an email to you.
Okay. Okay.
So participants, any query from your side? I think Pradeep ji, no query. So thank you so much for your time and wonderful session on the biomedical modeling through simpleware software. So thank you so much.
Okay. Thank you, sir. So in future, if you have any kind of requirement of related to
A session on 10 a.m. So now you can leave this meeting and tomorrow you may join us. Thank you.